Good afternoon, everyone, and welcome to the Texas Space Grants Consortium's Design Challenge Showcase for Spring 2021. My name is Tim Urban. I'm the director of the Texas Space Grant Consortium, and with me online are Talia Jurgens and Angelica Cruzinga. If you have any general questions during our showcase, please contact us at designchallenge@tsgc.utexas.edu. We'd like to welcome all the student teams that are online on our Zoom webinar today, as well as all the faculty advisors, NASA mentors, and other guests who are joining us on YouTube Live. Now, before we begin, I want to pause for a moment to honor the memory of Ken Ong, professor at Lamar University, who passed away this semester. Ken was the first faculty I met at my very first showcase in 2013, and he has been a longtime supporter of Texas Space Grant. His presence will be missed, and his impact will continue to be felt by the students and all the others he supported. Thank you, Ken. Okay, welcome again. We have 10 video presentations today from 10 teams and another 10 tomorrow. We'll have our opening speaker and then 3 sessions of student teams. Each team will have 10 minutes for their video and then a 10-minute question and answer period. For questions, we are using the Slido app, so slido.com. Enter the code TSGC, and that way you can upvote questions or ask questions to our opening speaker as well as to all the teams. Here's our schedule for today. The 3 sessions, 4 teams in the first session, 3 in the second, 3 in the third. Again, for any general questions, use the Design Challenge email address. And for the Q&A, please don't use the YouTube or Zoom Q&A. Use the Slido app, slido.com, passcode TSGC. Okay, it is my pleasure to welcome back to Design Challenge our guest speaker today, Heather Paul. Heather's an engineer at NASA Johnson Space Center. She began her education at Auburn University, getting degrees in mechanical engineering and Spanish. She continued at UT Austin, where she got a master's of science in mechanical engineering, and then later a master's degree in fitness and human performance from the University of Houston, Clear Lake. A lot of the students are interested in systems engineering, and Heather has worked on a lot of different systems, including life sciences, propulsion, mission operations, communications, human research, spacesuit, and tool design and development. And all those go along with most of our projects here today. She spent a large part of her career engineering, developing life support systems for the next generation spacesuits. And she's currently with the Orion program as a health and medical technical authority for the crew and service module. So I'm very pleased to welcome back Heather Paul.
Hi, everyone, and thank you, Tim, for that lovely introduction, and thank you, Angelica and Talia, for also inviting me here to speak with all of you today. I am super excited to be your opening speaker for what is definitely going to be a very engaging and exciting event. All of the teams have worked hard. I've worked with this program for several years, and it's always impressive to see the level of effort, continuity, creativity, and innovation that goes into your project. So before I even get started with what I want to share with you today, I just want to say congratulations to all of you on all of your efforts, and I applaud you for engaging in a program like this to get the experience so that you learn a little bit more about what kind of engineer, scientist, mathematician, or just human being you want to be with your career as you start to move on past your education and decide what you want to do to develop or engineer your path forward. So today, as your opening speaker, it's just my pleasure to be here with you today. I am calling in from my home office here in Houston, Texas, where I have been teleworking for the past year plus, but still getting our missions, our development activities, our technology, our hardware being built for these next generation missions with the multi-purpose crew vehicle. Specifically, I work with the Orion program. And today you might be expecting a bit of a technical presentation, but really what I'd like to share is a lot of the story of what I've done as an engineer and as a scientist for NASA over the last 25 years of my career here. So with that, I am going to share my slides with you and let's get started. Okay, so Tim, if I could get you to just give me a thumbs up or unmute and let me know that you can see the slides.
I see the slides. You're good to go.
Awesome. All right, we are live from Heather's Mission Control in Houston, Texas. Okay, so as Tim mentioned, I'm a mechanical engineer. That is my undergraduate background. So a lot of what I'm going to be talking about today is really my experiences as an engineer, but there are probably some experiences that I'm going to share with you that might surprise you as far as what you think of that a NASA engineer would do in his or her day-to-day career. Now, before we even get one moment further into my presentation, I want us all to just take a moment to sit with ourselves. I'm getting all, exercise, health and wellness at the moment, but that's also what I do for my night and activities in the weekends. Just take a deep breath in with me, breathe in that fresh, clean oxygen that we have, and exhale away and just release. Well, we should all take a moment to appreciate the beautiful Earth environment that we live in that provides us with that precious oxygen. Because when it comes to human exploration, the engineering, the science, the innovation that it takes to send humans to places like the International Space Station, the Moon, Mars, wherever we decide to send you, there are a lot of key things that we have to provide to keep you alive, healthy, and well. With that said, I want you to all just take a moment and look at the picture on the slide here. If you feel inclined, you can close your eyes. I just want you to free your mind. Don't worry about anything else going on because I'm going to show you a word. And when I show you this word, I want you to take a moment to put a visual image, an image in your mind as to what you see when I share this word with you. What do you think of? What images does your mind conjure up when you think of the word engineer? Now, I have done a lot of presentations around the world to students just like you, and typically the answers that I get is an individual working in a lab, working on a vehicle, maybe looking at plans. Now, if you notice, though, the last set of slides was a bunch of what type of human being? A male figure. Well, for both the men and the women in the audience today, I'm here to share that it is a very diverse population of engineers that we work with. And some of them grow up just like this picture here. That is me growing up in a very artistic family. So my mom was a school teacher. My dad was a counselor. My sister, who you see here in the middle, she works in communications. And here I am growing up loving math and science and saying, I want to be an engineer for NASA. Better yet, I want to be an astronaut for NASA. Mom, dad, friends and family, how can I make this happen? Well, from a very young age, it was very clear that I was very different from my family members. And so in art class, when some students would draw pictures of their families, their pets, their homes, instead, my pictures were always like this, of the solar system. Now, I can't take credit for this piece of art. This is from the internet because, let's face it, ladies and gents, mine was way better. This isn't even to scale. That's a running joke I like to say, but truly, I loved learning about the solar system, imagining what it would be like to be one of the lucky people who gets to go and explore space and just learn all about these different things: asteroids, comets, black holes, satellites, planets, solar systems. I was heavily influenced by the science fiction movies and books that were all around me. In high school, instead of going out for spring break with my friends, I went to Huntsville, Alabama to our Marshall Space Flight Center and spent a week learning all about the different types of engineering and science that go into the space program. I went to space camp. Then, also in high school, I was a science ambassador to Russia. This is a picture that I hold dear to my heart because it's me in the Russian Orlan spacesuit. We'll come back to what this picture means to me in the future. But thinking about how we develop these human systems so that people can safely and successfully explore beyond our Earth atmosphere. As Tim mentioned, I went to Auburn University in Alabama, and I graduated with 2 degrees, a Bachelor of Science in Mechanical Engineering and a Bachelor of Arts in Spanish. There's that creativity, that artistic piece. And I started working here at NASA at the young age of 19 years old. I was already developing kits that we could send up to the space station to understand more about the human body and physiology changes in space. And then as I continued through my education, I learned more about what type of mechanical engineer I wanted to be. I got a Master of Science from the University of Texas at Austin, hook 'em horns. And then I went on to get a Master of Arts in Fitness and Human Performance at the University of Houston, Clear Lake. And then in 2016, because of my extensive outreach efforts on behalf of our NASA workforce around the world, I was given an honorary PhD at the University of Strathclyde in Glasgow, Scotland, for my efforts in particular at that university to engage students, both men and women students, to become engineers. So with that, that's a very brief background on my education and really how I ended up here at NASA. And now it's time to get into the serious part of my conversation with you today. So I have a series of very technical questions. I hope you're going to play along with me and really think about it when I ask you these things, because we're about to talk serious engineering. So first question. Who likes to clean? Now, I can't see you, but if you like to clean, you can lift your hand up in the air. You can point at yourself. I'm going to just imagine that, there's a handful of you that are there saying you like cleaning. Little confession about me, I do not like cleaning at all. Thank you, Joe Patrick. I see you raised your hand. Excellent. Well, when I became a project engineer and a project manager here for NASA, I had to figure out how to not only design, develop, test, and fly hardware, but really what levels of cleanliness were required so that hardware that we developed here in labs and spaces on Earth could not only fly to the International Space Station, but keep the environment safe for our crew members. So I worked a lot on the vehicles or the tools and development of hardware that we had to build the space station that took us about 10 years to construct. But I really had to learn a lot about cleanliness levels and had to do a lot of my cleaning myself, even today with the hardware that I send. Now, what about working in teams? Anyone like teamwork? I hope your answer is yes, because obviously you've been working on your teams with your projects, and that, you can go, that some days go really well, and then other days maybe not so well. And in fact, with a lot of teams, you often have natural team leaders and even team followers, and then the cheerleaders. I have been all 3 of these, and it's critical to really understand that teamwork is a very, very intricate process and a big part of our space exploration missions. What you see here is the Mission Control Center here in Houston, Texas, and all of these people have teams of support crew. For every one individual that you see in a seat in our front control room, there are dozens, if not more, team members supporting them in labs and facilities and offices around the world. A huge team effort to successfully implement not only what's happening on Space Station right now, but all of our exploration programs that are definitely under development to get us back to the moon and eventually on to Mars. So whether you're a team leader, a follower, or a cheerleader, or all 3, definitely I encourage you to explore what those different team capabilities are and see how you can best be a good team person. What about wearing a uniform? Sometimes I talk to students and they're required to wear uniforms to school. Well, I can tell you that we require our astronauts to wear very, very specific life-saving uniforms called spacesuits. This is the advanced crew escape suit that we used during the space shuttle era when the astronauts were on board the space shuttle launching from Earth or returning back home. What we have done for our Orion program is learned the lessons of this particular suit, and what you'll see our astronauts wearing for our MPCV or multi-purpose crew vehicle missions, like you see here, is something very similar to that orange suit, or as we lovingly call it, the pumpkin suit, because let's face it, you kind of look like a pumpkin when you're in the orange suit. So this is our MPCV or multi-purpose crew vehicle. The Orion crew capsule is at the tippy top. It's big enough to hold 4 crew members for up to 21 days. And here are 4 of our fellow crew members in some of our testing that we do right here at the Johnson Space Center, and that's me second from the right. What you see pictured here are 2 engineers, well, 3 engineers, myself, and then someone who actually works in biomechanics in our lab to look at the kinesiology, the biomechanics behind what it takes to keep the human alive inside of the suit. Different tests that we've done, we have the neutral buoyancy laboratory here at the Johnson Space Center, which is a big swimming pool where we have sunk underwater different piece parts of the space station to train our crew members for their extravehicular activities. But we also use the top side of the pool for very important operations, like on landing day with our Orion missions, we will be landing in the ocean. How do you make sure that your crew members, the 4 inside, can successfully get out of the vehicle if they have assistance or if they don't? So, you know, some days as an engineer here at NASA, I'm not just sitting in office spaces and conference rooms. I'm actually a test subject, or as I like to call myself, an astronaut simulator, so that I can understand, because of my stature, my physiology, my strength, my energy levels, I'm a good astronaut simulator to see what it's going to feel like to live and work within the systems that my teams and I are designing. As Tim mentioned, I spent a lot of time doing life support engineering for the spacesuit. This is the current spacesuit that we have right now. And we have a facility here at the Johnson Space Center where we can offset you using a huge crane to put you in what we call reduced gravity. So levels of gravity like the moon or Mars, or even offset you almost as closely as we can get to microgravity. There are so many different types of engineers that it takes to design these systems. And I mentioned earlier one of my friends who is a biomechanical or biomedical engineer. So the previous picture was me inside of the suit. And then here you see me just in tank top, workout gear, doing the same exact operations with all of those little reflectors on my arms and legs to study really how does my movement change when I'm suited versus unsuited. When you wear a spacesuit, it is a lot of work and effort. We call it exercising within the suit, and it really is. So we have to look at the biomechanics, the body movements, the physical exertion that our crew members are going to undergo when we're designing these spacesuits, so that we make sure not only they can survive, which is rule number 1, that they can do their job successfully, which is rule number 2, but that we can also prevent injury. So if you were paying attention, I said we were going to bring this picture back. This is the Russian Orlan suit. So this is the Russian version of the extravehicular mobility unit that our crew members use on the space station. And I mentioned that I love that picture because I was still in high school when I started learning about all of the different complexities of designing spacesuit systems for human beings. And at that point in my very early education of engineering, I knew I wanted to work for NASA. I didn't know I was going to spend a large part of my early to mid-career developing things that you see right here, spacesuits for us to go and explore. So you never know when these experiences that you get, like working in this program, working on these projects, could inspire you to engineer that career to your next destination. Now, if you're paying attention, a question just came up. Who likes to travel? I love traveling, and one day I hope to get back to traveling to places like the pictures right here. Now, ladies and gentlemen, this is me on Mars. And if you've been paying attention to our space program like I know you have, you know that this is photoshopped for sure, because We haven't sent humans to Mars yet, but we have sent robotic precursors. As a health and medical technical authority, my job is to keep the humans alive. There is a whole span of people around the world that are developing our robotic precursors to send to these destinations where we eventually want to send humans. And that is such a critical piece so that we can learn and test and understand our environments to better develop our human systems so our humans can survive. Now, for those of you in science and engineering, you've probably spent a lot of your time doing experiments. I loved doing experiments when I was growing up in high school and college. And now the best part about being a NASA engineer is that I also get to be the person being experimented on. I mentioned earlier, I'm a test subject for NASA, which means I do spend a good chunk of my time in spacesuits, in labs, simulating the very things that we're going to ask our crew members to do on the space station and eventually with our Orion missions. So this is a pretty fun day in the life of an engineer right here. Sure, let's get in the spacesuit for several hours, test out how well the gloves work when we're using our tools. In this case, I'm wearing the spacesuit that we wear when we're on the space station going outside for our spacewalks. But certainly I've had a lot of experience working within some of the other suits that are under development, and also going to places like our mock-up facility. This is a mid-fidelity mock-up that we have at the Johnson Space Center, and we've done a tremendous amount of activities that we call HITLs, human in the loop testing. When you are a human systems engineer, systems engineering and integration, all of those things, you gotta get the humans in the test to see how well all of your designs that you've worked on so hard on paper actually work. So here you see my good friend Laura behind me. She's a fellow engineer as well. And we were working on the winch system to open up the top hatch. What we discovered in this test is the way that the design worked was great, except it took several, like dozens, if not 100 cycles of the winch just to open the hatch. So was it a successful human in the loop test? Absolutely. Did we learn a lot? Yes, for sure. And since then, we have changed up that design to make it so that the ratio of the turn isn't as much. We don't need to do 100 turns. That's a lot of upper body work. It's now down in the tens range. I've also been able to sleep on the job, which is super fun. Yes, we have slumber parties here at NASA. We actually call them tests where they're analog missions. We put a couple of people like you see here into a small chamber and see how well they behave. How well do they get along? More importantly, how well does that life support system scrub out the carbon dioxide and the water that the humans are creating and refresh or revitalize that atmosphere with good, clean breathing air and oxygen? If you noticed in that last picture, I was the exercising test subject, and I mentioned early on that by day I'm a NASA engineer and I'm a health and medical tech authority keeping our astronauts alive and thinking about how the designs could improve or challenge our crew members for these exploration missions. By night, I teach group fitness classes, strength and conditioning, yoga, Pilates. I'm a health coach and a health and wellness professional as well. So I really understand the ties of human physiology and keeping our human beings alive, whether you're my human beings here on Earth or human beings in space. And whether you have your feet here on planet Earth or up on our space station, you have got to exercise. Exercise is key in microgravity because it doesn't take long before your cardiovascular system degenerates, your bones deteriorate, your muscles deteriorate. And we want to make sure that our crew members that we send not only to the space station, but to the moon and beyond, will then, when they come home, will land safely and be able to go back to normal activities of daily living. So on the space station, we have several gym facilities, including a resistive exercise device to do your typical weightlifting activities like squats, deadlift, and bench press. You also saw Sunita Williams running on our treadmill on the space station, so they can maintain their cardiovascular endurance. Here's a few more pictures of me, sweating for science, as I like to call it, where yes, I do VO2 max testing here to test out, make sure that physiologically I am still comparable to the crew members that we send into space. And then doing all of these different activities to look at if there are ways that we can simulate or replicate the physical deconditioning that we see on the space station and for these future missions if we weren't to exercise the way that we do now. So that exercise piece is absolutely critical. Well, we also have a bicycle ergometer on the space station. So you'll notice we've got a treadmill, a bike, a big resistive exercise device. But when you think about the Orion capsule, that's really just like a big camping vehicle. You've got 4 people camping out, so to speak, for 21 days. We don't have room for all of these different devices. So certainly we are looking at ways to maximize the very tiny volume that we have on the Orion capsule and maximize the type of exercise that we can do. We can't fit a treadmill in. We could possibly fit an exercise bike, but here's what we're looking at doing, at least for our early missions, looking at rowing as an exercise modality and then changing a rowing device into a strength and conditioning device. This is an engineering challenge for sure. How do you get all the different things that you can get into resistive exercise and cardiovascular exercise into the equivalent of a tiny box that's about the size of 2 car batteries? These are some of the fun challenges we're facing. So we've talked about experiments. What about learning by experience? You're learning by experience by participating in this design showcase. Hopefully you've definitely learned a lot about yourself and the projects that you've been working along the way. Sometimes our experiences, we get asked to do things that maybe aren't as easy to talk about. One of these experiences is a test subject and a Sweating for Science contributor here at the Johnson Space Center is I have in fact provided human body donations in the name of science. Well, what does that mean? If you look here, this is what water does in space. It forms these beautiful bubbles, and it's really fun. The astronauts love to play with it to some extent, but water is an absolute precious resource. When I asked you to breathe in and out at the very beginning of my presentation, we talked very quickly about the importance of having enough oxygen to keep you alive. Well, you got to have water as well. The human body is primarily made up of water. We've got to supply that water and keep you hydrated. But when you're sending water to space, it's heavy. It costs a lot to send up into space or to the moon. So we have to come up with ways that we can recycle or reclaim the water out of all of the different fluids that we have being developed on the space station. And yes, that includes the fluids coming out of the human body. So on the bottom left, you see our water reclamation system on the space station. This is huge. So right now with our exploration missions, we're probably not going to do much water reclamation, but we are looking at ways to do that for the sustainable presence on the lunar surface. Now, the next few pictures are, just a kind of public service announcement here to talk about that sometimes the experiences that I've had here as a NASA engineer have benefited life on Earth. And that is a big piece of what NASA is all about in terms of our vision and our values. So I have used a lot of the lessons that we've learned developing water reclamation systems and water recycling systems for space so that we can help underdeveloped and underprivileged communities like in Rwanda, Africa, where we have sent some of our Engineers Without Borders teams to put in water filtration systems, water collection systems, so that during their monsoon seasons, they can collect the fresh, clean water, keep it fresh and clean, and hopefully allow some of these young engineers and scientists in the picture with me to grow up and be our international partners for our space exploration missions. So sometimes learning by experience allows you to give experiences to others, and that is such a critical piece of paying it forward as a NASA engineer. Now, I don't know if any of you like history. History was one of my worst subjects in school, but learning by experience can sometimes bring history to life. So the next few pictures, I want you to try to figure out what's going on here. So I'm in a very special suit. I kind of look like the lunch lady, really, right? I'm in a bunny suit, which means we have to protect the equipment that I'm looking at. I'm pointing at a plaque that says AP11. Can any of you guess what AP11 might stand for in the history of our NASA missions? Well, hopefully, AP might stand for Apollo program and our critical mission, Apollo 11. Of course, we should all know historically what happened then. Boots on the moon, which is what we're trying to get back to for 2024. The next man and the first woman setting step back on the moon. Super exciting piece. Well, so now in order to make these missions successful, we have to go back in time and look at all of the successes and maybe some of the failures, definitely the failures of the lunar missions that we did back in the 1970s. So what I'm holding for you is a very highly technical piece of equipment. It's a brush. That's right, the Apollo 11 brush that was used very simply. Now, this isn't Apollo 11. This is one of our later Apollo missions. But look at how dirty our spacesuits got when we went to the moon. That's just a fact of the lunar surface. That regolith gets everywhere and absolutely gets within the seams of the suit and into the suit system as a whole. So back in the Apollo days, we used a very simple brush to do the best that we could to brush off the lunar regolith from the suit so you didn't bring as much dirt inside. Boy, oh boy, learning from history is a great experience because there are things that we did really well back then and things we could definitely learn from. I mentioned the Neutral Buoyancy Laboratory. Here is the bird's eye view of the facility. And you can then see the huge swimming pool where we have some of the ISS or International Space Station modules sunk underwater. I showed you that we do the topside evaluations with our high fidelity mock-up for the Orion capsule. If you're one of the lucky people who gets to work with the crew members and train them for their spacewalks, like I did in my early and mid-career, and you have a scuba certification, you can dive underwater in the Neutral Buoyancy Laboratory and watch real time while the crew members are working with the hardware that you've designed and developed. Very fun stuff. Sometimes our experiences include travel. So we have to figure out ways that we can simulate these missions, but we can't send people to the moon to do that. So where here on planet Earth can we go to look at things like craters and see what extensively it would take to send our human beings, our astronauts, down into these craters? We did a lot of this kind of work in places like Arizona, Meteor Crater, Arizona, back in the Apollo days, where we took our Apollo astronauts out there with geologists and engineers, and we did simulations to go through some of the activities that we were going to ask our crew members to do, deploying seismic experiments, taking lunar samples, bringing samples packaged properly back to Earth. All of these different experiences help us make our mission successful. And this is one of my favorite experiences. So if you're ever on an aircraft, hopefully if it's doing this, you are strapped into that seat. Otherwise, those oxygen masks are coming down because you are diving towards Earth. Well, this is a controlled environment. This is one of our test platforms called the C9, or as we lovingly call it, the Vomit Comet, where depending on the trajectory, that path, that sinusoidal wave that our pilots are so trained perfectly to take us through, you can introduce levels of reduced gravity. So here we were doing some of our spacesuit tests in lunar and Mars gravity. I've also spent extensive amounts of time in microgravity. And I can tell you, I've done push-ups here on Earth. I've done push-ups on Mars and the moon, and they're super duper fun, but no push-ups are as fun as they are in microgravity because you don't even need hands. You just use your feet to project you up. So sometimes when you're a really good scientist or engineer during these missions, these flights, and you finish up your experiment early, you get a little bit of opportunity to do some fun things. You know, science when you're floating around is the best kind of science that there really is. So as we close up here today, before I get to your questions, the final question, and this is probably one of the most important ones, is who likes to share with others what you've learned? Well, this is a big piece of what I think is our obligation as NASA scientists and engineers, to take the lessons that we learned through all of our experiments, through experience, through travel, yes, even through cleaning hardware to get it ready for space, and teach students just like you around the world about all the different possibilities. Maybe open your minds to all of the different things that you could become as a part of our International Space Program. A couple of final reflections. So not only is it important to share what you've learned like I'm doing with you today, but it's also important to reflect on, why are we doing all of this? This is a beautiful view of the space station with Spaceship Earth in the background. And we do this because human beings by nature, we are meant to be explorers. We're innovative, we're creative. If you ever grew up like I did, constantly asking my friends and family, my teachers, my mom, my dad, why? Why do I need to do this? Well, here is why. Because it is innate in our human nature to explore. And what better way than through exploring our planets, our moons, our solar systems, but getting humans there is complex. It's tough. We have to feed them. We have to give them oxygen. We have to make sure that we are keeping the environment such that we don't have too much humidity or too much carbon dioxide. We have to figure out how to grow foods because, sure, we can send up foods that are packaged, but over time, human beings love those fresh fruits that we send up. We have to develop cold storage systems like the freezers here so that when we're doing our science samples, whether it's collecting regolith from the moon, collecting Mars samples, or even collecting human samples to see how healthy our crew members are doing, how are we going to keep those viable in our space environment? And so much of the work that our astronauts do right now on the space station is all of this. They are our construction crew. They are our maintenance crew. You know, we've got a big home and a national laboratory rotating around our planet right now. These astronauts are doing hundreds of experiments for our scientists here on Earth. They're learning how to give us information so that we can develop better systems for our human beings. And yes, as you see Peggy doing here with one of our ocular health experiments, they are our test subjects to really understand how the human body adapts. We are amazing electrical mechanical systems that adapt to our environment. Sometimes that's good, but sometimes, like with the physical deconditioning that we see with microgravity, it's not good. So how can we track our human physiology and make sure that our crew members are going to be able to not only successfully survive and do their missions, but also come back home to their friends and family and be able to share their stories and teach us all about what we're doing for space exploration. I love these final few photographs. Of course, if you're looking and you've done your geography assignment for today, you know that this is Italy. It's just to show you that there is so much work that we're also doing to observe our own planet as much as we are looking beyond low Earth atmosphere where the space station is right now, but observing life here on our home planet so that we can preserve this very precious spaceship that we are all on together. This is a picture of the Texas coastline, and I'm waving to you from Clear Lake, Texas, which is up kind of at the top part of the screen. Our astronauts love to look at these photos and see their home from space and realize that one day they're going to come home and have all of these wonderful stories. But as you get further and further away, when we go back to the moon, it takes a couple of days to get there. Depending on what we decide for our mission plans, they might be there for a handful of days and come back. But what about setting our sights even beyond what we did with the Apollo missions, even beyond what we're planning to have boots on the moon for 2024 and send humans to where our robotic precursors are right now on planet Mars? These are questions that our engineers and scientists around the world are working on right now. And if this is something that is exciting to you, that you have questions about, whether you want to do the human piece like I do, or whether you want to do the robotic piece like so many of my friends and coworkers do, this is important stuff to think about. And I encourage you to think about everything I've shared with you today. Hopefully, I've opened your mind up a little bit to the many different aspects of engineering that I personally have been able to do over the last 25 years. And I encourage you to think about that because really, we have a lot of places that we can go. We've got a lot of great work going on right now, and it's up to you to engineer your path forward. I love this quote by Dr. Seuss. You have brains in your head, you have feet in your shoes, you can steer yourself in any direction you choose. You're on your own and you know what you know, and you are the one who will decide where to go. And finally, Maya Angelou, I am here today talking to you as one, but I stand as 10,000, if not hundreds of thousands of engineers around the world who over the last many decades and many decades to come will continue to make our space missions, our human missions, our robotic missions possible so that we can do amazing things as we explore. And so hopefully you've been able to see yourself in some of these pictures. I can tell you that I have had many people who doubted that I would make this into a career. I had people when I was looking at colleges and universities tell me as a female, I would never be successful in engineering and to look elsewhere. And I am very, very happy to say that after 25 years here at NASA, I think I have proved those people wrong. And it's because I had the bravery, the desire, the passion, the energy, and the can-do attitude to engineer my career. And I encourage all of you to do the same. So with that, I'm going to stop my presentation. Thank you all so much for listening to my story today, and we'll open it up for any questions that I can answer.
Thank you very, very much, Heather. That was very inspiring. On behalf of our 100 students and all our guests online, thank you so much for coming to speak with us. So to all of us, everybody online, please ask your questions at slido.com. Use the code TSGC, and you can upvote and view other people's questions. While we wait for a few questions to come in, I've got many of my own.
Okay.
So I love that last slide with your face here. I think you've definitely shown that anybody can make it that far. So how would our students get their foot in the door if they haven't had anything except this space grant experience?
That's a great question, Tim. Thank you so much for asking. And so, when I talk about the international space community, so I specifically work for NASA. So I am a government employee. And so you can go to the nasa.gov, short for government website, and look for ways to apply for jobs. So there's a number of different ways. If you're still in school, you can look, and they call it something different from when I was growing up. So I was a cooperative education student, but definitely I think even if you go to your favorite search engine and just say, how can I get a job at NASA, it'll probably land you to a couple of different sites for NASA specific. I do also really want to give a shout out to our contractor community, Lockheed Martin, Boeing, even SpaceX, our commercial partners. Because we have now expanded into the commercial realm, there are even more job opportunities out there. So certainly when you think about working for NASA, it's much bigger than just government employees like myself. And each of the different contractors and commercial partners have their own requirements and desirements for your educational background, your work experience. So I think the number one thing that I can encourage all of you to do is think about what it is that you think you might want to do. Maybe do some research on your own to look at how you could apply for jobs. But most critically, before you even do that, get your work experience. I was a student for NASA through undergrad and my graduate terms, and it gave me so much insight into, I thought I knew what kind of engineer I wanted to be. I was absolutely certain I was going to be someone developing satellite systems and rockets. I mean, sure, everyone wants to be a rocket engineer, right? Rocket scientist. And I learned very early on, I didn't want to do any of that stuff, because as soon as I started working on spacesuits and tools and hardware that the human beings are going to work with and construct, I thought, oh my gosh, I just love life support. I love physiology. I love human performance, figuring out how we can develop tools and hardware that the astronauts use to live and work. And so because of that work experience, I was able to basically strike out the things that I thought, wow, I actually don't want to be a rocket scientist. I want to be a human systems engineer and a mechanical engineer for human systems. So get as much work experience, ask questions of people, get to know people like me, and find mentors in the community to learn more about what they do and decide for yourself, that looks cool, let me give that a try.
Excellent. Thank you, Heather. We have a lot of questions online now.
Great.
So the first one is, what's been your favorite mission to work on?
That's really hard, because I've worked space station, I've worked future development, and now I am hot and heavy in the Orion program. And I got to say right now, it's pretty exciting, because we are getting ready to fly Artemis 1, which is our uncrewed Orion vehicle. So that is set to take place later this calendar year. And then in a couple of years, we're actually going to send our first crew up on Artemis 2. And so that's really the mission I'm focused on, because again, I'm a human person, right? So I got to make sure I have a crew to keep healthy and alive. So that Artemis 2 mission, it's maybe 2 years away, but our hardware is built and at the Cape and at Cape Canaveral and Kennedy Space Center. And last year, before we went into lockdown, I was able to go and see her. And I was just like, it's amazing to think about. And yes, it's a girl. I get props, you know what? Yes, absolutely. Our Orion vehicle is there and ready for the crew. And it's just, we've got a couple of things left to do to test and put our hardware in. And it's just super exciting to see that.
Excellent. Excellent. It's great to hear about what you're doing now. This next question goes back in time. What job did you have when you first started work at 19?
So great question. And I love this because my first job at NASA was not at all what I thought I wanted to be. Remember, I wanted to be someone developing the hardware, the rockets, the satellites, and I got put in life sciences. Life sciences, so human, physiology, learning about how the body changes in space. And at the time, as much as I grew up exercising and dancing and doing all of these very human physiology-like things, I really didn't enjoy physiology or biology. And so I really did a big thumbs down at first when I came to NASA. I was like, really? I got to work with human beings and learn about blood and urine and feces? Blah. I don't need to talk about that. No way. But over the course of that 3-month period, I learned so much that, again, without that experience, I wouldn't have realized that those are the very things I love to talk about every single day. And I have a joke with my team. As a health and medical person, if there's a day in my job where I'm not talking about those human outputs and human systems, right? So blood, urine, fecal matter, vomit. Yes, I talk about all these things on a day-to-day basis. And if I hadn't started in life sciences, maybe my path wouldn't be where I am today. So that first job was all truly learning about what kinds of tests that we have in space at the time with our space shuttle missions and early thoughts for space station. And then really understanding how to design blood collection kits for space that will keep the blood in such a way that it's preserved. So when we bring it back to our labs here on Earth, we could analyze it.
Very good. Thank you. So sort of related to the first question, what's been your favorite NASA design project to work on? So other than Orion, other than your first job, is there something else you really loved?
I loved my work with the Spacesuit team. I had the opportunity to work not only on the pressure garment, which is the material layers for that, basically encapsulate the human, but also the life support system, that big backpack that sits on your back typically, that has all of your oxygen, battery power, communications. That is systems engineering at its best, because you have to have all of those different systems working together to keep the human inside alive, able to do their job and injury free. And so it was just so much fun learning about that. And then from my perspective, thinking about the human performance aspect. When I went to University of Texas at Austin, I was a mechanical engineer who had a biomechanical engineering advisor. And he put me in classes like physiology, cardiovascular dynamics, biomechanics. And I asked him one day, I said, why I need to be in fluid dynamics, thermodynamics, heat transfer. And he said, yeah, all of those are important too. But if you're going to be someone who designs systems like spacesuits, you have to understand the biomechanics, the electrical and mechanical systems of the human body, the physiology. And those were some words that, again, as I mentioned, have these conversations with your faculty advisors, with your teachers, with mentors, talk through these things, because had I not been advised to take all of those classes, I don't know if I would have had the education and the foundation to realize that, sure, I'm designing life support systems that are very mechanical, fluid dynamics, but my critical thought is to keep the human person alive inside. So much fun.
Excellent. Excellent. Yeah, we appreciate all the work that you do to keep our astronauts safe. Next question relates to astronauts. So I think you mentioned this early on. Have you ever wanted to become an astronaut?
Oh, yes, I have applied. And, obviously I got beat out by other people who are very, very highly qualified. So I'm probably past the point where I'm going to apply for the next version, but we'll see. You never know. You got to throw your hat in. But, it's a huge competition. I was in the application pool where we had over 18,000 applicants. And I believe that selection, they chose 12. So even just to be considered is pretty awesome. But absolutely, I would love to go. If they, you know, slapped a spacesuit on me tomorrow and said, "Good luck, Heather, we're sending you to the moon," I would absolutely say, "I am on my way."
Excellent. Yeah, those are pretty long odds, 12 out of 18,000.
Yeah.
How many times have you applied?
Officially once, although unofficially more than that. So what I mean by that is, you know, basically looking at the considerations. I wanted to make sure that I actually really met all of the criteria, so I wouldn't be one of those people that applied and wasn't eligible. So I did wait until I was fully eligible and then some. And so I wanted to make sure my application was absolutely concrete. Now, I've known people who have applied tens of more times. And certainly, you know, everything that I've been told is it's just like life. You got to just keep trying. So the stakes have been pretty high with our last several crews. And certainly when I look at the individuals that they select, they are just outstanding, stellar individuals who each of them comes with their own unique set of capabilities and skills. And then when you weave them together, what an amazing team. There is probably one job in this life that I would not want to do, and that is being on the astronaut selection committee. Because if you think about those 18,000 candidates, sure, there were probably some that weren't eligible, but there were a lot of people who are highly, highly credible and eligible. How do you hone that down to getting a handful of people? Those are some tough choices to make for sure. And really, it's an honor, you know, being a test subject for NASA. I think that's about as close as I could get to being an actual astronaut. I work with the astronauts closely, and I'm a test subject. So they actually put me in these tests, in the suits, in the test environments, in the labs, and trust my assessments when I come out of these human in the loop tests. So that in itself is a big honor. So, you know, I say it jokingly, but really not so much, that those of us who are test subjects are astronaut simulators.
That sounds perfect. Yeah. Yeah. So let me ask a follow on then. So as a test subject, do you spend more time in the suit, or would an astronaut?
That's a great question. So we have our astronauts, and they are not always under training at times. You know, sometimes they actually have office jobs just like the rest of us, and they are in lockstep with our design crews. So there's, you know, a small selection of astronauts at any given point who we can call upon to be our test subjects, and we absolutely do as much as we possibly can. But our test subject pool is probably bigger than that. And so certainly a lot of times what we do, it's just like engineering. You test and then you test again. So with our engineering test subjects like myself, sometimes we'll go in and we'll do a preliminary test, even just to run through the operations, so that when our crew members come in who have very limited time, just a handful of hours, our operations to do the simulation or the test or the experiment is very clean, very thorough, and we can get the crew members in and out. So it's a bit of a tricky question. You know, we're all a big team. And so definitely we have our engineering test subjects, and then we love to take advantage of the crew when we can get them into our labs and experiments, especially flown crew members, so that we understand they can think back to their experiences in microgravity. And then even our newer astronauts who come from Air Force, Navy operations, they bring all of that expertise and experience to us as well.
Excellent. Thank you. Talking about the spacesuits now, have there been any breakthroughs from the orange suits to the new Orion suits?
Yes, absolutely. So there are definitely a lot of similarities, because there were a lot of breakthroughs when we first developed that suit from some of our early Air Force suits. So the Orion environment is going to be pretty different from the Space Shuttle launch and reentry environment. Obviously, you know, on launch day, similar; on landing day, kind of similar. Our Orion missions are going to land us back in the water, so very similar to the Apollo mission and some of the SpaceX missions that we've had here, where they land in the ocean. So some of the capabilities of the suit, it really is meant to be a survival suit. So looking at the materials, the bladders, the life support, the secondary oxygen bottles that we have, the helmet design, For smaller framed females like myself, sometimes being in the original size of the suit, the helmet is really huge. So we actually have developed a smaller helmet for those of us who are more on the petite size of the spectrum. So again, constantly reiterating designs, learning from our successes and less successful projects from the past to make these developments happen in the future. Now for Orion, we also don't have spacewalks planned, but obviously for the lunar missions we do. So our design and development teams for our exploration spacesuits, or what we call the exploration extravehicular mobility unit, are definitely learning not only from the pumpkin suit designs, but especially from our current EVA extravehicular activity suits.
Okay, great. And how about comfort level? How has that evolved?
Oh my goodness, so much so, yes. So one of my friends used to call himself a spacesuit crash test dummy because he was one of our earliest test subjects in the suits, and he has the bumps and bruises to prove it just like I do. So looking at, and that's why it's important to have a whole different set of test subjects like me. So I'm more of a petite framed female. I fall into the lower size demographic of our astronauts, but we've got really tall guys, really big buff guys who also get in our suits too. And so understanding the design considerations of that pressure garment, again, the materials that surround the crew member, looking at the mechanics of the joints. Way back many, many years ago, we started realizing that we were actually getting shoulder injuries in the suit, and we had a huge investigation to kind of figure out why is that so. And we just learned that because of the design of the suit, the hard upper torso, the fiberglass shell underneath it, that it was actually impinging on certain individuals' shoulder joints. Here we are with physiology again, right? Human performance of the crew member inside of this suit. You got to understand how that shoulder joint works, the range of motion, the muscles of the rotator cuff, and then look at the spacesuit joint placement to see, well, maybe we need to have different sized fiberglass shells underneath, which is what we ultimately did, so that we don't get that shoulder impingement. And I could talk for, oh my gosh, several more hours about all of this. Again, I just love the spacesuit design and development that I was privy to. I've moved beyond that now, but we've got so many great people still working on that project. It's so fun and interesting. And our next generation spacesuit for lunar surface exploration, it's going to be so much more mobile than our Apollo suits were.
Excellent. All right, we've got another question here. Are there any techniques besides this design challenge showcase for developing our technical communication skills? So where can the students go and present and become awesome presenters like you?
Thank you. Practice, practice, and practice. I will openly admit, guys, I talk to myself all the time. I do. I'm just a talkative person. And certainly since we've been in lockdown, my goodness, I have a lot of conversations with myself. And I say this jokingly, it is true. It's when I disagree with myself that we run into problems. But when I'm getting ready to do my technical presentations, I'm standing up in front of people who have had even more experience than me. And I get nervous too, and that's okay. You got to practice. Take the time to put your thoughts down on paper, practice, get with friends and family, bore them to tears with your amazing brilliance. Get the practice, take advantage of experiences just like the showcase here, and spread your wings. The more that you can get that work experience, the more you can get that practice, and communication is a big piece of all of this. I mentioned teamwork. You got to be able to work in teams. You also have to be able to communicate and share what you've learned with others. So if it's not something that comes naturally to you, you got to practice. Practice makes perfect. Actually, I like practice makes permanent. You are an amazing creature that will adapt to your environment. There are skills that you can learn. You just have to put the effort into it. And if presenting and communicating is something that comes naturally to you, that's awesome. I bet you can still hone those skills to become better and better every single time that you get the opportunity. So just get out there and get as much experience, as much practice as you can. And you know what? Talk to yourself. It works.
I think we have time for one more question now.
Okay.
So is there a particular piece of the Orion program that you're most looking forward to in the future?
I'm really looking forward to, so I mentioned Artemis 1. So that's the uncrewed test mission to make sure that basically the rocket system, the vehicle works. We will slingshot it around the moon and bring it back here to Earth safely. That's our uncrewed checkout mission. I'm super excited for Artemis 2 because obviously that's going to be the first time that our crew members will board the vehicle and actually go again, slingshot around the moon, for lack of a better term, and return back safely. Where things are going to get really super exciting is what we do after that, which is this boots on the moon objective to get the first woman I mentioned. Sadly, probably won't be me, but will it be you, ladies? Could be. And the next man back to the surface of the moon in the 2024 timeframe. So Orion is the taxi cab that's going to get us there. That's really the truth. We're developing the gateway system, which is kind of like a mini space station, and also our human lander system, which there was a big announcement made just a few days ago as far as which of our commercial partners was selected for that first option period to develop that lander. I'm not going to say it here. That's your homework. If you haven't heard the news, go search when you're done with your presentations today. Don't do it while people are presenting, though. You got to listen and pay attention, right? But anyway, so I'm excited to see what happens next, because as much as we've been looking to go back to the moon, I want to get us there and get to that human sustainable presence where we're there not for a handful of days, but weeks, months, maybe one day, years at a time. So I think there's a lot of excitement that's going to happen in this next decade. This is the closest that I've ever been to working in the space program and getting to the moon. And it gives me chills. Even as I'm talking to you guys about it right now, I'm ready to be, done and go back to work because I'm so excited. So it's fun.
Thank you, Heather. Thank you. Maybe one last question.
Sure.
Is there anything that you can recommend for the students to prepare themselves on their career path? Any last words of advice?
I encourage you, as much as I've talked about engineering your own career, don't do it so tight that you miss out on the opportunities that maybe don't look like they align with your path. Again, I mentioned my advisor who put me in classes that I really had no interest in that became the foundation of a lot of what I do today. And a part of why I am not only the NASA engineer that I am, but also the fitness professional and health and wellness coach outside of my working hours. I love that. I love bringing health and wellness not only to my crew members here for the space missions that I work on, but also to our workforce and frankly, my friends and family. I had a vision that I wanted to be an engineer for NASA. I originally wanted to be an aerospace engineer. And so I started engineering that career path. And I had very, very specific opportunities and mentors and direction along the way that took me off of that path into the path that I'm on today. So as much as I want you to set your eyes on what you think you want to do when you grow up, when you become an engineer or a scientist or whatever your future holds, keep your eyes and ears open to opportunities that might challenge you. These might be things that don't even look like they're appealing to do, that could take you on a whole new, amazing direction. So I think with that, that's really my advice. Have an idea for what you want to do, but keep your eyes and ears open for those opportunities that might lend themselves to even greater opportunities for you in the future.
Thank you so much. Always inspiring, always a pleasure. We'll have you back maybe right after Artemis 2. We'll hear all about that mission. That would be great.
That would be amazing.
So thank you, Heather. We are going to take a quick break now and start our students at 1:05. So you've got time for a quick bio break. Thank you so much.
Bye, everyone. Heather. Thank you so much. Best of luck to all of you.
Okay, welcome back to the Design Challenge Showcase. We are ready to start our team presentations. Again, each team has 10 minutes to show their video and then 10 minutes for a question and answer session. Everybody can use the slido.com app, so slido.com, and submit your questions there. The code is TSGC. You don't have to wait for the end of the video. Go ahead and ask as soon as you have questions for the team. So team members, you are going to be promoted to panelist for the duration of your talk and your question and answer. Please keep your videos off and stay muted until your video is over, and then you can come on screen. Our first team this afternoon is University of North Texas and Team Lit with the Advanced Spacecraft Lighting Control System.
Team Lit presents Advanced Spacecraft Lighting Control System.
Traditional lighting systems in spacecraft offer only one constant setting. The continuous bright white light confuses the crew members' biological systems into thinking it's daylight all the time. The body starts to feel stressed. Certain hormones aren't releasing while too much of another hormone are releasing. This internal mechanism is called our circadian rhythm. Our senior design team proposes a solution to optimize the current lighting system's ability to maintain the circadian rhythm for each of the crew members. My name is Farhan. I am the team lead, front-end designer, and hardware specialist. We have Simmer. She is our back-end software specialist. We have Shafi. He is our algorithm specialist. We have Shitij. He is our network specialist. And we are Team Lit. Our motto is to keep it lit. Our teammate Shafi will start with our objectives in the next slide.
Thank you, Farhan. Let's recap our objectives to our project. 1. Circadian rhythm cycle, to maintain the circadian rhythm for each crew member. 2. Plant and vegetation cycle, to provide a 2-stage plant growing routine. 3. Logging system, to restrict any unauthorized access to the system. 4. Color correction, to detect and attempt to correct any color degradation. 5. Light intensity, to maintain the light's brightness. 6. Voice command system, to change the light settings with a voice command. 7. Graphic user interface, to increase usability. Our teammate Jitij will walk you through our overall system design in the next slide.
Thank you, Safi. We have our overall system component design for the project here on the slide. The user interface will be used to control the system. The server uses a SQLite database to store all the data. The voice control uses an IRI speaker, array microphone to listen for the voice commands. The networking interface uses a router to link the entire system. Raspberry Pi for controllers are used all on the lights and the main console. DMX lights are used to illuminate the light zones. A custom PCB was designed for the sensor system. These are the main software we use to accomplish our project. Now Simmer will dive into the implementation behind the design.
Thank you, Jitij. Let's talk about what's happening behind the scenes here, shall we? How is the circadian being maintained? For this, I would like to ask my teammate Shafi, the algorithm specialist, to give us some idea.
The circadian cycle takes in the time zone that the user configures where the lights will adapt throughout the day according to the expected color schedule.
Thank you, Shafi. Let's see what's next. How is the growth and bloom cycle working? This also calls for our algorithm specialist, Shafi.
Our growth and bloom cycle for plants and vegetation follows the same principle as the circadian cycle with a different color schedule. However, the user has the ability to select the colors for the day and night as well.
Thank you, Shafi. Now, how does the autocorrect system work for color degradation and light intensity? For this, I would like to call our backend software specialist to answer. Whoops, I guess that's me. Our color degradation and the light intensity correction system occurs at least once every hour. It utilizes the color sensor system, which includes an RGB color and lux sensor, to compare the sensor values with each expected value An attempt is made for an adjustment if there's any significant variances between the values. The system also notifies the user if there's any error. Now that we have some idea about how the behind scenes work, let's look into the front end. Starting off with how does the dashboard and the login is being implemented. I would like to call our front-end specialist, Farhan, to tell us about the dashboard. But before that, let me cover the login part real quick. To access the dashboard, the user must register to be able to log in. There's also an administrator who has the privilege to delete user, grant users to become either an admin or technician, otherwise all the users are general users. Now let's ask Farhan about what's inside the dashboard.
The dashboard allows the user to monitor and control the zones. There is a diagnostic panel that is available to the admin and the tech users to be able to perform reboots of the zones, system updates, and access usage logs.
Thank you, Farhan. We can't forget about how the voice command is working, can we? Let's call our network specialist. Hey Chitij, how is the voice command working?
The voice command system listens for a command where the server processes the command to generate an intent and will perform the action requested.
Thank you, Chitij. I know this slide was a lot of information to take in, but it was an imperative step before the next slide. The next slide will give you a visual demonstration of our system.
Hi there, we're Team Lit, and today we'll be demonstrating our lighting control system. Let's take a look at the parts that we have today. Each of our zones features an LED light, and it's controlled by a microcontroller that's mounted to each of the lights. And it's utilizing a USB to a DMX converter, and all of the lights communicate through our router system here. Let's take a look at a live demo. I've already pre-wrote the credentials. I'm just going to hit login here. And we're going to see this actually takes us to an admin panel. And we can see all sorts of different users that are able to access the system. We can go to the dashboard. And we're greeted with the welcome screen. This is the main command center. We're able to see which of the zones are connected to the system. We have a fun little time clock here. We can sign out of the system, and there's even an emergency shutdown feature. Let's interact with one of the zones. Let's turn off the room lights. So I'll select the menu from here, the navigation panel, and we're going to just pick one of the zones. And the first two presets is going to be to maintain the circadian rhythm for our crew members. And then the second two presets will be a two-stage plant cycle. Let's take a look at what me and Jill Green can do. Let's pick a growth cycle.
Adjusting lights to growth cycle.
And then we even offer a manual control system if the user needs to override the system. They have the ability to do so.
Adjusting lights to warm light.
Now let's take a look at the voice command system. Hey Jarvis, change the lights to circadian 1 for Nora.
Adjusting lights to circadian. Crew member A.
Success, it works. Thank you for joining our presentation today and demonstration.
Now, wasn't that lit? Thanks, Farhan. To conclude our results, we have a GUI created with the hashed logging system, admin, and diagnostic panel, referred to as the LIT command center. All the lights in the local network used OLA to transmit DMX signals, a routine to maintain the crew members' circadian rhythm, a custom PCB for sensor system designed, prototyped, and manufactured, referred to as the LIT detector, a voice command system created, referred to as the LIT commander, a plant environment was used to grow tomatoes, and mustard plants using the plant lighting routines.
For the future development, we envision additional features that can be added, such as voice recognition, motion sensing, as well as email notification to enhance the usability of the system.
We would like to take a moment to acknowledge Dr. Tim Urban, Ms. Talia Jurgens, Mr. George Salazar, Dr. Robin, our lab manager Alejandro, and the Department of Computer Science and Engineering at UNT for providing us with this opportunity. These are our references.
Thank you.
Thank you.
We will now be taking questions.
Okay, thank you, Team Lit. You can all turn your cameras on, unmute, and we have some questions for you. Again, to the audience, submit your questions for the team to slido.com, and the code is TSGC. All right, welcome, team. The first question we have here, two-part question. Is the login system you described typical of NASA systems, and who should be controlling it, the astronauts or mission control?
I'll take that one. So the login system that we have created, it is for a typical NASA system. So we have our main dashboard GUI, which will be there, and then for the what was the question again? I'm sorry.
The second part, who should be controlling it, the astronauts or mission control?
The login system, the crew member in the spacecraft will be controlling it, and there is an admin and a technician. So an admin will have privileges where the admin can make someone else as an admin, and the admin will have a control of who can control the system in the spacecraft and who cannot.
Okay, next question. Do you have a feature or plans to access the system through other devices other than the touchscreen?
Yeah, absolutely. That's actually already in place. We actually have a QR code system that'll be placed on all of the lights, and the user can actually scan the QR code and be able to access the application from a mobile device. You can see right here, I have an iPad here, and if I just hit login here, it should take me directly to the page. I gotta type in the password. But anyways, you can access the system through a mobile device, and anybody else can use the system.
Excellent, thank you. Next question, were you able to grow the plants?
I can answer this question. So we were having trouble with growing plants after the snowstorm because we didn't have power as well as water for a week. So we added different color temperatures so the user can select to optimize which light is adaptable for the plants to increase the growth. Because different color temperatures offer different color spectrums. So some plants did not survive after the storm, but actually, let me show you the other plants that turned out to be working better using the new color temperature.
While he's grabbing the plant, I got the system to work. My Wi-Fi had hopped off, so you can actually access it from an iPad.
Okay. And then these are the plants. As you can see, this is the chili, and this is a sweet basil. So as you can see, it's healthy. So after the storm, the chili turned out to be really great. And then no yellow leaves or anything. So it's growing perfectly using the new temperature. So these are the plants. Let me go ahead and put them back.
Excellent, thanks.
So actually have it in my room.
Next question, does the voice command system need access to the internet to function?
I can take that. No, it doesn't need any internet to process the command. It's like we use a Raspberry, which is like an offline voice assistant toolkit, where we can just train the assistant to recognize a certain pattern of words and like commands. Then after it recognizes a certain like patterns, then you can just process the whatever action you want to take. So it doesn't need internet access.
Okay, good. And then another question about the system. Do you have a wake-up word for the system, and can it be changed?
Oh, yeah. We do have a wake-up word. We use like Jarvis. Like we had some other options too, like Siri or like Google, Alexa or something, but we use Jarvis because it sounds more cool and like more unique. And if you don't know or not, Jarvis is the name of like Iron Man's AI, and we all are like Marvel's fans, so we just decided to use the Jarvis. So if you say like, hey Jarvis, then the system will wake up and you can proceed with the commands.
That's perfect. Then you could say, hey, Jarvis, or hey, Siri, and they can talk it out.
Yeah, you can say like, hey, Jarvis, turn on this light on this zone, and it will turn it on.
Next question, can you add new lights or zones to the system?
Yes, we've set it up for scalability. As of right now, we can do up to 7 zones. We can add additional zones, but with the network hardware that we had available, we were only able to test up to 7 at the moment.
Okay, good. And then as far as the light, what frequencies did you pick? Did you pick natural sunlight, or did you optimize for some other conditions?
I believe Shafi can answer this one. He was the one in charge of all the algorithms for the color scheduling.
So for the color for the circadian rhythm thing, we used Kelvin temperature throughout the day because it kind of used a similar routine as the plants, but the circadian rhythm cases, we use different Kelvin temperatures, and according to each hour, it makes the transition to the lights. And then for the night dark stage, we decided to do a red RGB value instead of pitch black. So for more in details, like if you're interested in what color temperature we used, starting from for the Kelvin temperature, it starts off like 1800 at 6 a.m. and then it goes to the highest 6300 at noon, and then it decreases the same opposite pattern until it reaches the 6 p.m. and then it goes to the dark stage.
Okay, another question on the lights here. What was the cost per light?
The cost per light will be roughly around like $100 per unit. And then that's minus like all the sensors attached.
Okay. Question on the potential. So do you see any potential for using smaller, lower power microcontrollers for each of the lights?
Yes, absolutely. Once the system is optimized, we can determine how much memory usage is happening, and then we can utilize a microcontroller that's more compact, suited for the necessary requirement. The server would require the most amount of memory available, as it's processing a lot of different commands as all the lights are communicating back to that server. But the independent zones, you can get away with a much smaller controller.
Okay, and let me ask all of you, so what has been your biggest challenges so far this semester? I know we're in the middle of a pandemic, we had the ice storm, but maybe take turns and talk about your biggest challenges.
Sure. My biggest challenges was designing the PCB system for the sensors. I started all the way from the designing phase to prototyping. We prototyped using a CNC machine. We were able to mill out one of our prototypes, and then we even sent a service request to China to be able to have our PCB boards actually manufactured. And then we were able to create our actual sensor system here, and it runs off of a battery. And then go ahead, team. What else did y'all learn?
For me, the biggest challenge was to set up the voice thing, and the first I was having some trouble like listening. The system wasn't listening to me at all. Like as soon as I overcome that challenge, and it was like easy after that. And the second problem that we all face is the integration. Like we were working on our separate thing, like but at the end of the semester where we came up and like we tried to integrate, it was giving a lot of bugs. So it probably took us like 2 or 3 weeks to like totally integrate and make the system running like perfectly. So it was also the biggest challenge.
To go with jitters, my favorite, my challenge was the login system itself. In order for the login system, we created a different file. And for that to be connected with the SQLite database that we have on our Node-RED software, it was really hard to connect all of that. That took actually a lot of time, and there were troubles and errors and stuff. That was the biggest challenge. And then to go off with jitters, integrating that with the Node-RED, where our dashboard is, it was one of the hardest things to actually get it to work.
So for me, the biggest challenge I faced with while I was growing the plants, because this is the first time I was actually growing plants from seeds. And then based upon like the different weather, especially the snowstorm, that no lights and everything, it was really difficult to grow the plants, because initially the plants were growing fine, and then when the changes in temperature, it impacted the lives of the plants. So like for some plants were not improving, and then the others after the storm were like survived. Like we had to do like basically I had to do like to see that how different routines can change the plant's growth. So this one was like the biggest challenge I faced throughout the semester. And
okay, great. Well, thank you very much, team. Great project. Glad you came through the winter storm okay, and your plants did as well.
Thank you for
Thank
having
you.
us back.
Thank you.
thank you.
Our next team is from Texas Women's University. It's Team Athena 5, and they are working on the prevention or mitigation of headaches in space.
Good afternoon from Athena 5. I'm Vanessa Parnell, team lead, and we're representing the School of Health Promotion and Kinesiology from Texas Women's University in Denton, Texas. Our faculty mentor is Dr. Rigby, and NASA mentor is Dr. Easter. And now Elizabeth Shatta up next with a recap from last semester.
The problem they faced was an uneven fluid distribution in microgravity environments, which caused an increase in intracranial pressure leading to headaches. The solution was to create a heated calf sleeve which would draw blood down from the head and chest to the lower extremities. Upon testing the calf sleeve, they found that the temperature of the calf increased, promoting vasodilation of the vessel and thus supporting their hypothesis. This semester, we chose to go a different direction and focus on removing carbon dioxide, or CO2, from the blood, which is another alleged cause of headaches. With the increase in CO2, there is an increase in lethargy and intracranial pressure. Acute exposure to elevated CO2 concentrations on the ISS are reported to deteriorate complex decision-making. Effective decision-making is critical to human spaceflight, especially during an emergency response. There are several conditions on the ISS that cause headaches. On Earth, the force of gravity pulls the body's fluids down towards the legs, while in space, the lack of gravity causes a fluid shift upwards towards the head and chest. This fluid shift presumably results in an increase in intracranial pressure, headache, and swelling. Along with fluid shifts, the astronauts are exposed to high levels of CO2. On the ISS, the maximum allowable concentration of CO2 is 5,250 parts per million, which is 17 times higher than on Earth. This effect is compounded when astronauts stay in one area for a period of time or when they are sleeping. Exposure to high levels of CO2 leads to a condition known as hypercapnia, which is a high concentration of CO2 in the bloodstream. This condition can cause headaches, dizziness, and fatigue. Dehydration is another issue astronauts face on the ISS and is a contributing factor to headaches. Dehydration can cause a decrease in sweating, resulting in an increase in core body temperature. The increase in core body temperature causes a decrease in pH. In other words, the blood becomes more acidic. This decrease in pH reduces hemoglobin's affinity for oxygen and increases the ability of CO2 to be transported throughout the body. The elevated levels of CO2 in the ISS, combined with the body's increased ability to transport CO2, make headaches a very prominent issue that astronauts face. To combat the prevalence of headaches in microgravity, NASA has attempted several strategies, and here's Yuzik Rodriguez to explain them.
Some of the strategies include pain relief medications such as Tylenol and Advil, which are reported 64% of astronauts take. The Russian Chibi-suit was a device that drew fluid back down to the legs. This was to counteract the tendency of fluids to accumulate in the head and weightlessness. Cabin fans, especially in areas of congregation and during sleep, are currently being used, preventing CO2 bubbles from forming around the astronauts. Filtration systems such as the carbon dioxide removal system ejects carbon dioxide, allowing for an environmentally safe cabin crew. Another possible solution to alleviate headaches in space is cooling. On Earth, cold therapy for headaches has been a long-used remedy due to its ability to treat pain and inflammation by inhibiting warm-sensitive neurons in the hypothalamus. By cooling, we are also able to induce vasoconstriction, which is simply vessel constriction, therefore decreasing vasodilation, which is dilation of the blood vessels, offset by the decrease in core body temperature. This would also induce venoconstriction, which is vein constriction, by contraction of smooth muscle around the veins, expediting carbon dioxide leaving the brain. Applying a frozen neck wrap at the onset of a migraine has shown to significantly reduce pain in individuals with migraine headaches. The problem we decided to address is the change of fluid distribution in microgravity, presumably leading to swelling in the head. We've identified excess carbon dioxide concentrations being a major contributor. Our solution is a mask to filter high concentrations of carbon dioxide and a gaiter to cool the neck in order to prevent or mitigate headaches. Now here's Emily Blanton with garment design.
The mask and gaiter are made from a product called Ecstatic, which is a blend of polyester, lycra, and nanosilver ion particles. The fabric selected ensures the garment stretches and is comfortable. The silver ion works as an antibacterial agent placed on the interior surface to combat the buildup of bacteria produced by the breath. The polypropylene exterior was used on both garments in order to wick sweat astronauts experience. Both garments come equipped with metal snaps and Velcro, so the astronaut has a more custom fit and can choose to wear the garments together or separately. Neck diameter, cheek length, and nose to chin measurements can be taken for a personalized fit for any astronaut. The garments have 3 mechanisms working to alleviate the amount of CO2 inhaled and expired by the astronaut. The CO2 filter selected works to limit molecules 0.30 microns and larger. A molecule of CO2 is 0.33 microns. The air purifier fan, which also has a filter in it, works to lower inhaled CO2, and the one-way valve's purpose is to lower environmental CO2. A 4th component was placed purposefully on the carotid to constrict the artery, reduce swelling, and lower core body temperature. The cryotherapy fabric is made of neoprene. It is antimicrobial, odorless, and uses a nitrogen gel to cool. The use of a cooling fabric instead of an intense cold allows for the astronaut to wear it for longer periods of time without becoming uncomfortable. Here's Ashley Short with our testing protocol.
In testing our product, the environment was set to mimic the atmosphere of the ISS. We found that it was most fitting to perform our testing procedures in a heat chamber to create a controlled environment with an ambient temperature of 75 to 80 degrees Fahrenheit and 60% humidity. The participant was lying in a declined position on the treadmill, assuming a 6-degree head-down tilt to simulate microgravity fluid shift. An ultrasound machine was used to measure the diameter of the left common carotid artery during testing. We chose this artery because it is one of the main arteries where blood enters the head. Before being exposed to any CO2, the participant's artery diameter was recorded for a baseline value from minute 0 to minute 5. This was defined as our normal environment. There was not much change in diameter. Then the participant breathed into a bag for 4 minutes without the mask on at 4,425 parts per million CO2, which is within the range of typical CO2 levels on the ISS. Carotid artery diameter increased in size, which was to be expected since CO2 is a potent vasodilator. Then the participant put on the mask. While being exposed to the same amount of ambient CO2, we noticed a sharp decline in artery diameter to a point even less than the values we recorded in the normal environment. This proved the mask to be effective in both isocapnic or normal CO2 and hypercapnic environments, and thereby aiding in reducing intracranial pressure via vasoconstriction. During our CO2 testing protocol, we measured end-tidal CO2 or EtCO2 non-invasively using a capnometer which detects the partial pressure or maximal concentration of CO2 exhaled. Normal values at rest are 5 to 6%, which is equivalent to 35 to 45 millimeters of mercury. As the CO2 was introduced to the participant, the end-tidal CO2 increased, indicating a significant increase of CO2 in the blood. The mask was then applied while being exposed to the same amount of CO2, and the end-tidal CO2 dropped back down into the range of normal values. This indicated that the mask was successful in filtering the amount of CO2 being inhaled and also eliminating CO2 upon exhalation. For testing the cooling wrap portion of our design, we had a participant perform vigorous exercise first to increase core body temperature above resting levels. Our goal in testing the cooling wrap was to prove it can help decrease core body temperature, therefore increasing hemoglobin's affinity for oxygen. After exercise, the participant entered the same heat chamber and assumed the 6-degree head-down tilt position. After lying down for approximately 30 minutes, we applied the cooling wrap and watched as the participant's core body temperature dropped. The environment for our cooling protocol was hotter than that of our CO2 protocol. This was simply to maintain the participants' elevated core body temperature to ensure that it was the effects from the cooling wrap that was helping decrease core body temperature. Back to Vanessa to talk about future direction.
We know that the cooling garment decreases body core temperature, but instead we would like to incorporate cooling copper plates. These will be battery operated and have the ability to conduct cool temperatures fast and effectively. The plates would be easily inserted on either side of the gaiter along the neck. We are also interested to see if the inclusion of the heated calf sleeve from the previous semester may have an additional effect. We re-examined alternate causes of headaches from the fall team, created a mask filter for CO2, and added cooling along the neck to reduce body core temperature, swelling, and intracranial pressure, thereby reducing headaches. Our acknowledgements. And now we'll take any questions.
All right, thank you, team. And I believe you are all online together. Is that correct?
Yes. Hello.
Welcome, Athena.
Hello, thank you.
So your team is unique in that this semester you've got the same topic, same team name, but you've got a completely different solution to it. So tell us about how you went from where the last semester's team started to starting over.
So basically, we thought that what last semester's team did was really good. However, we decided to incorporate cooling this semester just because when it comes to our body physiologically, there are actually a lot more cooling thermal receptors in our body, especially in areas such as our skin. So basically, if we implement cooling, there will be a greater response in our body, especially if we put it right here on top of the skin and on top of the carotid artery, then we would see a greater response contrary to heating. So this is why we decided to, go this route.
Okay, good. All right, questions are starting to come in. Remember, audience, please submit questions to slido.com. Use the code TSGC, and you can vote or upvote questions that are here. So first question, if blood flow is reduced below baseline, is there a risk of compromising mental function?
In microgravity, it works a little bit different than on Earth. So if we limit the amount of blood flow that's fed to the head, it's going to work completely different on a completely different plane than what we see on Earth. Physiologically, there's so much change happening. So I don't think that it would limit the cognitive function. Is that what we said? But I think the elimination of the CO2 is what we were really trying to address as far as that goes, to increase the cognitive function of the astronaut. And because the body acts so differently in microgravity when compared to Earth, limiting the blood flow was kind of one of our, a big focus for us to focus on.
I would like to add on to that. Actually, in microgravity, a lot of astronauts tend to experience things such as fatigue, lethargy, and they just cannot think properly sometimes because there's an increased blood distribution to the head. And this leads to things such as headaches, which is our topic. And so actually, on the contrary, it's actually going to help. Our device should help in preventing a lot of blood from entering the head.
Okay, and then your devices, the mask and the neck gaiter, are they meant to be worn during sleep or at any time?
We do, so primarily we want it to be worn like in sleep or when they're in small confined spaces or when they have a really high cognitive load, because it helps with that CO2 buildup that they can have. So it just helps reduce them and helps them have a clearer mind.
And actually, if I can add on to that, our team member Lizzie, she did wear it overnight, and the comfort level of the mask was very comfortable for her. So sleeping with it would actually be beneficial.
Okay, good. Yeah, we're no strangers to wearing masks nowadays, are we? So speaking of the pandemic, I mean, I see you are able to get together at least, so that is good. So what have been your biggest challenges this semester?
So I think for one, COVID in general has been quite the challenge. And then the snowstorm that I think affected all of us back in February, it kind of put a little damper in our testing. We were kind of set back a little bit with the timing of testing and stuff like that. And just trying to get a hold of different resources and different people, it was very difficult in some aspects to get in touch with to get the materials that we needed delivered, or get in touch with this person who was going to help us design, or just to make contact with people. So it definitely was challenging in that aspect.
I think along with that, with COVID and the snowstorm and being set back, I think we each personally had to get a little uncomfortable and out of our kines minds. I was the one who did the ultrasound testing. People go to school for that. I had to learn it in probably a few days, measuring vessel diameter. And Emily, if you want to share your time with SolidWorks.
So I was responsible for the design, and I learned SolidWorks within a month so that I could start designing our product as soon as we had the prototype to use for the design. So that was my biggest challenge, was doing something completely out of my normal day-to-day life. I was the tech subject, as Vanessa mentioned earlier, and I think the hardest part was just creating that high CO2 environment. It was pretty intense, just breathing that high CO2 air and being able to experience how the mask worked, though. That was pretty incredible, how much better it felt. But it was challenging.
Well, great. All right, we've got some questions now. So was there a noticeable reduction in the headaches? Or did you experience those while you were testing?
I would say the topic of headaches, one of the things that we struggled with was headaches being so anecdotal. It's very hard to measure how a person feels. We didn't ask Lizzie, are you experiencing a headache now? Are you experiencing a headache now? I think we knew the effects of CO2 on the body, and we knew that it can lead to a headache. And so we looked at the direct effects of vasoconstriction and focusing on just reducing the intracranial pressure, which we know can cause headaches.
And the decrease in the CO2 levels on top of that. Yes.
Okay, good. Next question. So how often does the CO2 filter need to be changed?
So both filters, the filter and the air purifier and the CO2 filter that's used in the mask itself, both need to be replaced within 60 days.
Okay. Are there other applications for your devices, non-aerospace, in which you feel your solution could be utilized?
Can you clarify? Does that mean on Earth? Are you talking about utilizing it on Earth, or?
I believe on Earth, yeah, as a spin-off, yeah.
Okay, well, our focus was actually not on Earth. It was mainly to use in the ISS, especially in confined areas. When the astronauts go and they do work in confined areas, CO2 bubbles can actually accumulate. So that was our focus. And then sleeping, and anytime that they're going to be in a confined space or working where they need, an extensive amount of cognitive load. So they'll need to mainly wear it on the ISS is kind of where we were going with that.
Okay, great. Well, thank you, team. It's great to see all of you together.
Thank you.
Thank you so much.
All right, our next team is from the University of Texas at Austin, the Space Spinners, and they are looking at a modified small terrestrial clothes washer for long duration space missions.
Hi, this is Team Space Spinners, and this is our presentation on our modified small terrestrial clothes washer for long-duration space missions. I'm Lila Bernhardt.
I'm Leonel Permel.
I'm Ariel Sweet.
And I'm Ashley Yang.
On current ISS missions, each crew member wears about 0.2 kilograms of clothes per day, which is made up of the normal clothes that last several weeks before disposal, but also workout clothes used in their daily exercise, which need to be thrown out every 2 to 3 days once they become dirty and start to smell. This is an unsustainable practice for long-duration missions, and NASA studies have shown that bringing a washing machine system with all of the required water and detergent is more practical and has a smaller equivalent system mass than bringing the disposable clothes. Because of all this, NASA has been designing zero-G washing machines since the 70s that have posed solutions to the major problems facing microgravity laundry. But since the 70s, terrestrial washers have also had several technological advancements and can now be very compact and energy efficient. The scope of our project is to identify a compact washing machine to modify and to run tests on to determine the feasibility of using a terrestrial washer in space.
Given our project background, we developed the problem statement listed here to summarize the mission of our project. TSGT also provided us with a short list of design goals for the machine. For one load, the washing machine needs to be able to clean up to 3 kilograms of clothing, use less than 30 kilograms of water, consume less than 750 watts of power, and have a total mass less than 60 kilograms. So the best way to meet the goals was to start with a machine that already came close to our desired results. We researched several different types of compact washers and selected the machine that best matched our needs, and we were able to obtain in a reasonable time frame. As you can see from this table, the machine initially met the target washer mass, power usage, and load size. However, the water usage was slightly higher than our target value. In modification and optimization processes, we strive to reduce the water usage and keep the washer mass and power usage below these thresholds. Once the machine arrived, we were able to begin experimentation to confirm the provided machine properties and to test different optimization methods. In order to run multiple comparable experiments, we used very similar sets of one cotton t-shirt and one pair of polyester dry fit shorts as our control load.
The first set of experiments we conducted at the suggestion of our project mentor was focused on removing as much water as possible from the wet clothes after washing. Doing so would reduce the amount of time and energy required of our sister team working on a terrestrial-based clothes dryer for similar applications to our project. To do this, our group first brainstormed a few ideas for mechanically removing water from the clothes. These ideas included inflating an airbag within the washing chamber to press the clothes against the side of the drum, pressing the clothes against the bottom of the drum using a plate and weights to simulate a linear actuator, and adding masses into the drum to agitate the clothes during the spin cycle. Although not especially feasible because of the added time it would demand of the astronauts, as well as the risk of flinging water that it would introduce, our group also tried wringing the clothes by hand to create an additional point of reference. In each experiment, the weight of the clothes was measured before the wash, before the spin cycle, after the spin cycle, and after the secondary drying mechanism. Each configuration was tested twice to generate a more complete data set, and throughout the experiments, the peak power draw, total energy usage, and water consumption were also cataloged. The results of the experiments showed a consistent pattern wherein the clothes absorbed about 3 times their dry weight in water before the spin cycle, and this spin cycle then removed water until the clothes were 1.6 times their dry weight. None of our secondary mechanisms proved noteworthy. The effectiveness of the spin cycle prompted us to investigate it more closely. By setting up a bucket and recording the mass of water extracted during the spin cycle against time, our group was able to arrive at some meaningful conclusions. In 2 different experiments, one run with the same clothing set as the previous experiments, and the other with the washer filled to its capacity with 3 kilograms of cotton t-shirts, the trend between water removed and time was initially linear before falling off at an asymptote just under twice the dry mass of the clothes. It was also observed in both experiments that 90% of this asymptotic value was achieved within 100 seconds and 95% within 2 minutes. From this, we could determine that spinning for longer periods of time would have severely diminishing returns.
To minimize the power consumption of the washer, we measured the peak power draw and energy consumption of our control load of clothes using a power meter. We ran several tests with customizable washing parameters, mainly focusing on the 5 different wash modes: heavy, gentle, soak, normal, and rapid. We applied peanut butter to dirty the clothes, and this helped demonstrate to us that some of the washing cycles were ineffective on their lowest settings, such as gentle and heavy, since they left heavy peanut butter smells and stains. Overall time of wash was positively correlated with energy consumption. We also learned that peak power for all wash modes was within the same 200 to 300 watt range, all during the ramp up to the spin cycle. The circled data points are of the rapid cycle, which both cleaned the clothes effectively and also consumed generally less power. After we finished our experimentation, we moved on to the second phase of assessing the washing machine. We started the deconstruction of the washing machine by removing easily accessible screws and then working inside out. The circuitry throughout the machine tied together several subsystems from the top and bottom, and we were able to remove it by unclipping or unscrewing circuitry at their connection points. We reached a blockage point where the tub system would not come apart through the removal of screws. Therefore, we decided to brute force cut through the plastic of the outer tub using saws, pliers, and bolt cutters, as you can see in the bottom left photo. Throughout the process of disassembling the entire washing machine, we were also categorizing the pieces by weight, material, and additional comments, such as electrical specs or part interaction. A large majority of the plastic parts are injection molded, and most of the metal components are bent stainless steel. These materials make sense due to their interaction with water and ease in mass manufacturing. From the categorization of parts of the washing machine, we came to the conclusion that there are some areas of optimization. One of our first changes would be to replace the current plastic and metal construction with lighter materials, such as structurally placed carbon fiber or titanium. This, with a modification to the tub size, would help us conserve energy in the system by reducing the moment of inertia. We also believe that some components can be replaced with higher quality and lighter substitutes, such as the main motor. For the user interface, the team recommends reducing the cycle choice to just 1, since it will decrease the amount of time crew members spend with the machine. In addition, modifying the washer for space use, we would first recommend creating a watertight seal for the lid so that water cannot leave the system. And second, we would recommend connecting a vacuum system to help reduce foam generation.
Through our design, experimentation, and analysis processes, our team selected a compact washing machine that had promising specifications of a low mass, volume, and power draw, which would meet our design goals. We were able to confirm each of these metrics through the measurement and experimentation with the machine, and later through the optimization. We began calculating how much we could lower each metric. In this chart, you can see the mass, volume, and power comparisons between the initial design goals and the 3 washer options. As you can see, while the regular washing machine has too large a mass and uses nearly the maximum power draw, the compact washer and the optimized values are significantly smaller than both the design goals and the home washer. The only design goal in which the compact washer fails is the total water usage. On the rapid wash small load preset, the washer uses an average of 33.2 kilograms of water, which is larger than the 30 kilogram goal. Steps and modifications can be made such that as the rinse water being held and reused for later washes, and this solution has been seen in previous NASA washer projects. These modifications, in combination with the lower specs of the compact washer, would meet all the requirements and would be a feasible design for microgravity use. Using the values laid out in the table on the previous slide, my team has started calculating the equivalent system mass for our trade-off analysis. For this, we have 2 more small tasks, which are to finish our disassembling and categorizing of the assembly that is still stuck together, shown on the slide, which will inform the mass optimizations, and characterizing the drive motor to help us inform our power optimization values. Following these last 2 steps, we will be set to complete the equivalent system mass calculations, assumptions, and comparisons for the trade-off analysis. Hopefully, this will show that the optimized washer is the best option for microgravity applications, and that these modifications be implemented and tested. Lastly, before the Q&A, future steps to continue this project would include computer-aided analysis to provide the maximum mass and volume optimizations, and to combine those results with low-gravity simulations or tests to prove that this concept would work in practice. Thank you very much for listening, and we look forward to answering all of your questions today.
Okay, thank you for the video, Space Spinners. And welcome to the Q&A. We've already got a couple questions here, so let me go through those. First question is, do you know what the maximum washer spin speed was?
Yeah, so we didn't have the opportunity to get a hold of a tachometer to officially check it, but we took the specification for its word that it spun at 900 RPM at a maximum spin speed.
Okay. Next question. What is the KISS principle you mentioned in your presentation?
The KISS principle stands for keep it simple, silly. We applied that in relation to the user interface because we really wanted to cut crew member time. So we don't want them to, have to decide on a wash cycle. And so our recommendation would be to just have rapid be the setting that they use when they're washing their clothes.
Okay. Other than water leaking from the lid, did you observe any other gravity-dependent features in the washer?
Yes, there were a couple other gravity-dependent features, including the drain pumps and the drain motors, as well as there was an overflow water lid. So just if the water reached a certain level, it would overflow and not leak into the electronics. So to fix that in microgravity usage, we would use different valves of some sort in order to lock off the inner tub so the water won't spill out.
Okay. Next question. What would you recommend to reduce the water consumption of the washer?
So our method to reduce the water consumption takes some examples from the previous background studies that we looked at through NASA. And so one of the ways that we can cut down the water usage by half is by you taking the water used in the rinse cycle during the wash and reserving that to be used in the subsequent wash during the wash cycle. And so that will cut down the water usage for each wash by half by using the rinse water from the previous cycle.
That's interesting. Very good. Are you able to estimate the amount of energy saved by reducing the moment of inertia with the spin cycle?
So in our preliminary calculations, the number that we've come up with is about a 20% saving in energy usage. That's through a combination of changing the moment of inertia through geometry and through different materials.
Okay, let me ask about the test you did. So how did you choose the clothes, and how did you choose peanut butter as your way to dirty the clothes?
So we chose the cotton t-shirt and the dry fit shorts because those are clothes that astronauts typically wear to exercise in space. And it's also, as we mentioned previously in our presentation, typically the clothes that gets the dirtiest for them the quickest because they're exercising at least an hour a day. And then we chose peanut butter sort of for two reasons. First off, from a lot of prior artwork, we noticed that they were using peanut butter and ketchup as ways of like dirtying the clothes. And then the second reason is just that peanut butter is super identifiable by smell and by look and by oil stains. And so once we washed through the clothes, we would do a sniff test and a look test to see if the peanut butter was still there. And that gave us really clear indications on whether or not the clothes were clean or not.
Okay, did you do any thoughts beyond the sniff test for future testing? Like if you had a real set of clothes someone wore, you would have bacteria there. How would you test for that?
Well, there are petri dish tests that we could do in order to see the bacterial content in the clothes after wash. But another test that we had considered but weren't able to complete for this would be to use color gradient to test the stains and how intense they were after each wash in order to choose which setting cleans the clothes most effectively for the power used.
All right, great. So what have been your biggest challenges this semester? I know you're compressed into one semester, so it's a fast pace, but just go through and give us some examples of your biggest challenges.
I think our biggest challenge is actually yet to come. We still have one small subsection within the washer that we need to take apart. We tried unscrewing it with a drill, and the bottom agitator plate will not come off the spline that it's attached to. So I think taking apart that final piece is going to be a toughie.
We do have plans to do that as our final steps before our final report that we will submit in about 3 weeks. So we plan to finish taking it apart so we can finish the mass optimization.
I would say, speaking more generally, one issue that we've sort of had to overcome with this project is just the very wide open scope of it. We were given, I think, 3 or 4 sort of target values, but apart from that, it was totally up to us to figure out what kind of direction we wanted to take this in and how we wanted to approach it. So narrowing that down into the testing procedures that we did, into the methodology that we did, that was a challenge, and our faculty mentor and our NASA mentor were really helpful in guiding us in those directions that we took.
I think another kind of pretty obvious issue is that we weren't able to really test the machine in microgravity, and so kind of having to infer how it'll react, and just kind of having to use different academic resources to kind of figure out how it will respond, and kind of figuring out what we might be able to use in order to kind of replace systems that wouldn't work in space.
Oh, good. Were you able to test it, say, on its side, or was it leaking too much?
The way that this washer was built is it wouldn't be able to wash on its side without the modifications implemented to make it work in microgravity.
Okay, good. And you mentioned that you worked with the dryer team. How closely did you work with them?
We didn't work quite closely because we each had separate design goals for the project, but we did talk to them about the tests they had been running and make sure to coordinate to make sure nothing we were doing was contradicting each other in what we were reporting.
Okay, perfect. Yeah, and trying to get the most water out of your clothes will definitely help them. That was a perfect compliment. Excellent. All right, one last question here from the audience. Do you think it would be feasible to have a washer-dryer combo machine to save space?
We do think that. In previous NASA designs, they'd actually combined both of them by having a washer for the clothes and then attached to that a microwave dryer so that the microwaves will dry the clothing instead of a physical tumbling. So what the dryer team is doing is to see how feasible it would be for a terrestrial dryer to work in space. But we think that microwaves might be more efficient. That's up to the dryer team to actually do those comparisons. But yes, we did consider combining them both into one product.
All right, great. Thank you very much, team. Good
you.
luck. All right, our next team is from San Jacinto College. It is Solar Focus. Their topic is a novel, non-tracking fiber optic solar concentrator for extraterrestrial applications.
Greetings, everyone. Our team is Solar Focus from San Jacinto College in Pasadena, Texas. Our team worked on designing a novel, non-tracking fiber optic solar concentrator for use on extraterrestrial habitats. Our team members are Pablo Reyes, Ian Ebert, myself, Carl Mena, and Kevin Saldana. Our faculty advisor is Dr. Nathaniel Wiggins, and our mentors are Christopher Mendel and Neil Jody.
Today is going to talk about a solar concentrator and how it uses a Fresnel lens and a funnel lens to concentrate light towards a focal point and then be harnessed as solar energy. I feel this design has potential for the main reason that it has no moving parts and thus eliminating some of the problems encountered in space, such as lunar dust.
The spherical lens, and to gain a basic structural and mathematical understanding of the Fresnel lens, I use Mathematica to code a two-dimensional model that transforms a spherical lens into a Fresnel lens. This model demonstrates how the lens reduces its thickness, which allows less light energy to be converted into heat energy. The Fresnel lens also increases the accuracy of the lens, although not shown in this model. When I started formulating the three-dimensional model using SolidWorks, I used basic Fresnel equations to form each rib along the 1 meter long design. The design was made using a prism shape for each rib in the Fresnel lens. This allowed for a reduction in spherical aberration, which is the error in the light accuracy of the light onto its focal point. A research study on Fresnel lenses shows that the efficiency of the lens increases up to 325 prisms, after which it begins to decrease. The high number of prisms allows the collection area, as shown in the bottom figure, to decrease in size, ultimately increasing the accuracy of the design. The equations presented on the right-hand side are altered Fresnel equations, used to optimize the shape of each prism in our design. Equations 1 through 5 can be used to find the range of transmittance angles from each prism. This allows us to calculate what percentage of the light will hit the outer edge of the funnel lens. Equation 6 uses the variables calculated in equations 1 through 5 to calculate the total transmittance through each prism. This equation allows us to optimize the interior angles and shape to gain maximum transmittance in our Fresnel lens.
The funnel lens is a vital component for the solar concentrator and requires a material that can withstand the extreme temperatures on the moon and simultaneously collect sunlight efficiently. For these demands to be met, we have established that the best material to be used is a transparent aluminum known as aluminum oxynitride, or ALON. It is worth mentioning that ALON has an outstanding refractive index of 1.79. The refractive index of ALON makes it possible to capture sunlight and send off into an optic fiber cable through a process known as total internal reflection. Total internal reflection is possible if and only if the refractive index of the medium from which light is coming from is less than that of the medium it enters, and if the angle of incidence is greater than the critical angle. The critical angle is obtained using Snell's law and solving for the angle of medium 1. This slide shows a ray trace of how light entering the funnel would reflect internally and lead towards the back, where it would then be fed into an optic fiber cable. And for that, we have Carl here to tell us more about it.
My name is Carl Mena, and I'm pursuing a mechanical engineering degree. And I oversaw the improvement of the optical fibers insulation. I decided to go with the MLI, which stands for multi-layer insulation. One of the advantages of the multi-layer insulation is that it can withstand temperatures that can reach 1000 Celsius, which in Fahrenheit is 1832. The multi-layer insulation is composed of multiple layers of thin reflective materials, and it's effective when it comes to reflecting radiation. The layers have in them materials that have a high thermal conductivity, and because of the conductive materials, it is effective in the high vacuum environments. One of the things I believe will improve the multi-layer insulation is that if we add the beta clothing, which is a material that NASA has used before on its projects, as an extra layer, if we add the beta clothing as an extra layer to the MLI, it would do a better job in outer space due to the radiation being abundant in the outer space environment. Not to mention that the convection and conduction are literally non-existent. The multi-layer insulation functions like this: by reducing the radiation heat by reflecting the radiant energy back towards the source of origin. Because some of the radiation can still get through, the process of adding multiple layers by adding the beta cloth on the insulation, it will increase the effectiveness of the insulator, which means less radiation will be transferred. By using the multi-layer insulation and adding the beta clothing onto the optic fiber cable, it would have a positive impact on the solar concentrator, and it will make it more effective in the outer space. Because of this, I believe that the optic fiber, once it's being insulated by the multi-layer and adding beta clothing as one of the layers, it would have more chance to withstand the harsh temperatures that they are present on the vacuum of outer space, making them last longer and being less prone to have difficulty or damages during its work. Next, Kevin Saldana with lunar dust.
Hello, my name is Kevin Saldana, and I'm here to talk to you about lunar dust. Lunar dust has been a long-time hindrance for many space missions, and it's one of the main obstacles many scientists and engineers have been trying to effectively overcome. One of the major problems that lunar dust causes is that its tiny particles can reach into the components of a motor and cause major damage, making these motors practically obsolete on the moon. The surface of the moon is filled with these tiny charged microparticles. Sending our solar concentrator without a proper way of dealing with the moon dust will render our device useless. To combat this, we have researched various ways to try and find a solution. The solution we felt best fit our design is to apply an electrodynamic dust shield that will repel the charged lunar dust from ever making contact with our device. This electrodynamic dust shield will be made of the material indium tin oxide and will serve as our thin layer of coating to protect against the lunar dust. The reason we chose this to be our EDS coating is because it's excellent transparency while being highly conductive as well. To power this EDS, it will require around 2 to 4 watts to keep the shield running no matter the size, large or small. Some test samples have shown to remove about 98% of the lunar dust, which is very optimal. This right here is a diagram of a test done by researchers showing off the effectiveness of the EDS. The bottom picture displays of how the shield works by employing an electrostatic and dielectrophoric forces to move particles across the surface. This last page shows off an extra specific properties of indium tin oxide. And that's it.
The image on the right-hand side shows our base design. We decided to use aluminum as the material because it is both strong and lightweight. We further decreased the weight of our design by using honeycomb structure, which allows us to drastically reduce the weight while keeping its structural integrity. The parabolic mirrors on the inner edges allow us to increase the surface area of the light that we collect by reflecting more light onto the Fresnel lens in the center. The lens in the center of the image allow us to lock our Fresnel lens in place, allowing it to withstand winds in extraterrestrial habitats.
This opportunity, and we today would like to extend a gratitude towards Professor Jody, Mr. Mendel, and Dr. Wiggins, because if it wasn't for you guys,
Okay, video ended there. So welcome, Solar Focus.
Yeah, hello.
Hello there.
Hello.
So audience, please remember to ask questions on slido.com. Use the code TSGC. I see most of the team. Okay, Ian is there as well. So Ian, I wanted to ask, you are returning. You're the one returning member.
Yeah.
How was that switching gears with a new team on the same project this semester?
You know, I had to kind of get them familiar with the background information for a while and then kind of pick off where we left off with everything, with the lenses. And, you know, it was definitely a problem that we encountered in the early stages of working on this, but we got to working on the project in a few weeks.
Good, good. I know you used a lot of software with this project. What were some of the learning curves on that software?
Right. I've been familiar with CAD modeling programs such as Inventor. I switched to SolidWorks because we're able to implement equations as parameters to create a Fresnel lens. One problem I'm working on and for future works, and hopefully by the final paper, is to implement the optimization equations to shape each of our prisms. I haven't gotten to that yet, but right now I can individually optimize each prism by hand on paper. So I'm just working on putting that in a 3D model.
Okay, and the rest of the team, how about your software challenges?
So on my end, I started off trying to make a funnel lens using Onshape, and at first it was really challenging because it was completely new software for me. I had never been introduced to it. So it did. I think that was probably just the getting started of it and whatnot. It was pretty tough on my end.
Anyone else want to chime in? All right, let me go to the questions here. Is there a concern with the Fresnel lens getting too hot?
Yes, there is, because of the extraterrestrial habitats have a wide range of surface temperatures. However, Alon does have a good coefficient of thermal expansion, so it's probably one of the best materials. It's not as brittle as materials such as like glass or plexiglass, so it's a lot more durable.
Okay, another question here. Is there any technology from another field of research that you think could be applicable or that you did apply to this project?
Well, I mean, Fresnel lenses definitely have a lot of studies done on them, and that helped us. They're not traditionally in a cylindrical shape, so we did use research from traditional like circle shaped Fresnel lenses. They're like flat plates to assist us with this, because there's a lot of companies that make those.
Okay. And then you spoke about the lunar dust, but you've also talked about different environments. So how would this change if you were doing it, say, on Mars compared to the moon?
Do you want to talk?
You got it, Kevin.
So we mainly focused around the moon. We didn't really take into account Mars, but for the most part with the moon, there's a lot of lunar dust that we have to take account for it, and the electrodynamic dust shield does take into account all this stuff and will, do its job by repelling this lunar dust and making it not touch the device.
Okay, that's good. So could it, in theory, power itself to keep itself dust-free?
Yeah. Like I said in the presentation, the EDS only takes about 2 to 4 watts of power, and our device should be able to self-sustain off that. Considering it doesn't take off, it captures more light energy and produces more light energy than it would need to power the EDS.
And it was indium tin oxide. Was that specific for the moon, or could it be used for any extraterrestrial application?
It could be used for a lot of different applications, not just the Fresnel lens and stuff like that. And it actually has been used for a lot of things. other than an EDS shield, yeah.
Okay. Let me check the questions here. So overall, again, considering the pandemic, the winter storm, everything, the whole semester, what were your biggest challenges your team faced this semester?
I think one of the biggest challenges was getting everyone up to par with the previous works from the previous team. Definitely learning some of the software such as Onshape to create the funnel lens. Yeah, that was probably the biggest one for me.
In my case, I think that one of the biggest challenges, and a very common one nowadays with COVID, I think that interaction that we had virtually, that lack of like just being there face to face to be able to explain some of the concepts talked over the semester, I think they could have been a lot better elaborated as in a face to face, and I definitely do believe that was a hindrance in the overall project.
Kevin or Carl?
In my case, I believe that one of the things that was a challenge for us, it was sometimes the lack of communication because like my partner Pablo said, we're not face to face due to the COVID restrictions and everything. So I believe that if we had been in person, we probably could have had more improvements. And again, it was a really good lesson that we were like virtually because it teaches us about teamwork. You know, sometimes when you join an engineering company, you have to do different things virtually. You can be, let's say, working in an oil rig in Saudi Arabia while your partners are in France in the headquarters, you know, and you have to do this type of situation where we do FaceTime or Zoom calls and everything and explain what's going on because they are not right there with you to understand what's going on in the situation. So for me, it was not only a challenge, but it was also a lesson because it taught me about the value of teamwork on how things might work in a nearby future when I'm working in an engineering company or something, you know. So that's for me, it was an obstacle, but also a lesson. I learned something new out of this situation. So win-win, we could say.
That's great. Exactly what we want you to get out of this experience. All right. Any last thoughts about your project or where you want to go from here?
I mean, obviously, I'm looking on implementing the optimizations towards the funnel lens. I have it mathematically proved and putting that in the final paper. Further optimizations on the funnel lens. And yeah, just try and get that into the final paper. That's our goal.
Okay, great. Thank you, team. Good luck finishing up the semester.
All right, thank you.
Thank you.
Thank you.
Thank you, sir.
Okay, that concludes our first session. We're going to take a break until 2:35, and then we will start with 3 more teams in session 2 and 3 more teams in session 3. All right, good afternoon. Welcome back to session 2 of the Texas Space Grant Consortium Design Challenge Showcase. I'm Tim Urban, the director of the Texas Space Grant Consortium, and online we also have Talia Jurgens and Angelica Cruzinga. If you have any questions or issues, please contact us at designchallenge@tsgc.utexas.edu, and we can help you out that way. Our next session kicks off at 2:35 with 3 teams. We'll take another 10-minute break, and then session 3 will begin at 3:45 with another 3 teams. Tomorrow we will have another 10 teams that will start at noon. First up for session 2, University of Houston, Clear Lake, and the Trailblazers.
Hello, and welcome to our presentation on the Quick Release Tool Atra Mark II, or Omnidirectional Tool Retention Apparatus Mark II, presented by the Trailblazers, Andrew Davison, Miguel De Leon, Colton Mateka, and Trevor Smith. Today's presentation contents are split into 3 major sections. Section 1, Project Goals, Criteria, and Constraints. Section 2, Modeling and Analysis. And Section 3, Testing Operations Plan, followed by a Q&A session. And with that, I'll hand it over to Miguel De Leon to present Section 1.
Thank you, Andrew. Now for Section 1, Project Goals, Criteria, and Constraints. For our project goals, we are to design a 2-piece quick release mechanism, test out the 3D printed prototype for its functionality, finalize the specs, manufacture the real prototype, test the prototype, and do the showcase at TSGC. Now for our criteria and constraints. We are to have a 1x1 4-hole square bolt hole pattern. It should be capable of holding 15 pounds of weight in Earth's gravity. It should require minimal force to detach a tool from the utility belt. All parts should weigh less than 2 pounds, and it should fit within a volume 4x4x3, and lunar dust should not impede the functionality of the system. The device should be easy to use. It should be operable outside the line of sight and by one hand. It should be operable with a large and bulky spacesuit glove. It should not have sharp edges or holes. The materials that we can use are aluminum 6061, aluminum 775, any series of stainless steel, and Teflon. Here for our materials and applicable standards, we have the standards for aluminum 661. We have NASA's system integration for operator reference when using the system. We have NASA's heat treatment for steel alloys. We have NASA's human integration design handbook. We have OSHA's occupational safety and health hazard standards. And here's our quality function deployment. Here, as you can see, we have our requirements, and we have our engineering metrics that satisfied it. We have our cost, weight of the device, volume of the device, force needed to detach the device, the 4-hole bolt pattern diameter, and the yield strength of the material. And now for our section 2, modeling and analysis, Andrew Davison.
So for modeling and analysis, we'll go ahead and start off with the isometric and orthographic views of the Atra Mark II, starting with the belt piece. The thickness, including the track width, is just over 5/16 of an inch, and the width and height are equal at 1.845 inches. Moving on to the tool piece, we can see that the thickness is 3/4 of an inch and that the width and height are equal to that of the belt piece at 1.845 inches. Seen here is a striking comparison between the Atra Mark I and Atra Mark II, emphasizing the vast size difference between the two. During a redesign, it was discovered that a large amount of space could be saved simply by moving the plunger from the belt piece to the tool piece. This significant design improvement allowed the Atra Mark II to be 6.5 times lighter and take up less than 1/5 of the space occupied by the Atra Mark I. The functionality of the Atra Mark II is simple. A female track on the belt piece guides a male disc piece into position such that a ball spring plunger can engage a detent and lock the given tool in place. In addition to the previously mentioned repositioning of the plunger, the Atra Mark II now incorporates a guide throat for imperfect alignment of the tool and belt piece, which should make storing the tool easier out of line of sight. As for pre-built components, a ball spring plunger was chosen as the retention mechanism, with the requirements that it have fine tolerances, have a suitable side force, and be easily replaceable. As with the Atra Mark I, the Mark II's plunger is a friction-bearing type, as it possesses extremely fine tolerances that would prevent dust ingress into the spring chamber. Note that the new plunger now utilizes a slotted head as opposed to the old plunger's hex head. The side force is the force that needs to be applied to remove the plunger from its detent, and ultimately is the force the astronaut would have to apply to remove tools from the utility belt. It's calculated with the simple equation that you see here, where the side force is equal to the spring in force divided by the tangent of the countersink angle theta divided by 2. In our case, the countersink angle was 73 degrees, and the spring in force, which was calculated using the spring constant and maximum spring deflection expected during operation, was 4.70 pounds. This resulted in a side force of about 6.35 pounds, which should be easy enough for the user to remove tools, but not so easy that they fall out unintentionally. And with that, I'll hand it over to Colton Mateka to explain our FEA results.
Thank you, Andrew. This slide shows the setup which we use to perform finite element analysis in SOLIDWORKS simulation. Not knowing exactly what tools would be used by the astronauts, we could not replicate a tool for the simulation. Therefore, we simulated the tool instead using an approximately 2-inch cube. The 15-pound distributed load could then be applied to the cube and transferred to the tool piece via the required countersunk screws. Additionally, the back of the belt piece was fixed in place to a flat geometry in order to simulate an interface with the utility belt. With the belt and tool pieces interfaced, performance of the Aurora Mark II could be analyzed. This figure shows the stress results or the stress plot developed from the simulation. Identified in red is the location of the max stress, which was determined to be 3.366 kpsi and occurred on the collar of the tool piece. Considering 6061 aluminum has a yield strength of 7.999 kpsi, the safety factor for the prototype was determined to be approximately 2.4. This satisfied our original goal of hitting a safety factor of 2. It is worth noting that we anticipated max stress for the prototype would occur on the belt piece along the slide. Although max stress for the belt piece did occur on the slides, the maximum stress occurred at the base of the slides. Additionally, the magnitude of the stress was only 1.526 kpsi, significantly less than the overall maximum stress presented on the previous slide. We do anticipate that a wider tool would generate a greater resultant torque, thus increasing the stress and strain along the slides and potentially causing the pieces to separate. However, as previously mentioned, it was never disclosed exactly what tools would be used by the astronaut. Considering the product requirements alone, this analysis did validate that the Aurora would not only meet, but also exceed the loading capabilities. I'll hand it over to Trevor Smith now to discuss the details corresponding to testing of the prototype.
Testing the Aurora was split into 3 sections. First, testing functionality in the presence of simulants. Second, its load supporting capabilities and required removal force. And third, its functionality and retention while performing simulated work. For the first test, we purchased 2 simulants, Martian and Lunar, from the Exolith Lab of the University of Central Florida. These simulants are trusted and purchased by NASA and reflect over 80% of the soil composition for each respective surface. Our main concern was simulant impeding the friction-bearing plunger, having a tolerance of about 25 microns. Specifications and particle analysis performed by the Exolith Lab show only 30% of the simulant particles could possibly intrude the plunger device. Testing consisted of 2 assembled Aurora prototypes placed in simulant, 1 in Martian and 1 lunar, then shaking the bag, completely submerging them. Then they were removed and cycled 10 times, being weighed before and after each test to quantify dust intrusion. In testing, the dust collected in surface gaps, slightly increasing removal force, but returned to its original state after being cycled and knocking off the dust. After cleaning the surface with compressed air, the devices only incurred an added weight of 2 to 4 10,000ths of a gram per each test. Next, a load test was conducted using the apparatus on the left, securing each component to their own wood block via wood screws. The female piece, on the block clamped to the table, had the throat of the device oriented up. With the Aurora interfaced, lab weights were added to an eye hook in the image to the right. Removal force was tested similarly, but with the female piece oriented down so the male piece could fall freely. The binding, caused by a moment arm shown to the left, interfered with the Aurora's removal test. The image on the right shows the addition of fishing line needed to apply tension, keeping the blocks level and removing the binding. Consequently, this binding requires the separation of the Aurora to be deliberate. The results of the testing shown largely agreed with our expectations, except not being able to test for the yield point, being limited in quantity of lab weights at our disposal. Nonetheless, the Aurora met or exceeded our requirements in these tests, verifying support of 30 pounds and a removal force of 6.21 pounds. To test the Aurora's ease of use and ability to retain tools, a maneuver test was performed. During this test, a Trailblazer simulated natural movements on an EVA mission by walking, kneeling, bending, and tool use, using large gloves. While removing and replacing tools to the Atra. The Atra proved effective and easy to use outside line of sight, requiring minimal force to remove and return to the utility belt. To prove the Atra does not require a retention device, we performed some ridiculous and extreme movements, all in Earth's gravity. While the cartwheel wasn't great, the Atra's ability to retain tools was. On behalf of the Trailblazers, I would like to thank everyone for their attention and open the floor for questions.
Thank you, Trailblazers.
Yeah, no
Love
problem.
the video of the extreme movements.
Yeah. Yeah, we were trying to, just think of things that astronauts are not going to be doing and not in as the extreme gravity that we have here, something that would knock the tools out. Because one of our criticisms, I think, from Micro G is they weren't convinced that it would hold the tool, that it could be knocked out without some type of locking device. And we were like, nah, I don't think so. So
that was good. Have you been in contact with them this semester?
No, we weren't selected as one of the people to move forward, unfortunately. So
it looks like a great design. I might just say, hey, we've got a new version. Take a look at this.
I mean, that would be great.
Yeah. All right. So audience, go ahead and ask your questions on slido.com. Use the code TSGC, and you can view and upvote questions there. In the meantime, let me just double check. So you used lunar and Mars simulants in your tests. Is that correct?
Correct.
Okay. And did you see any performance difference between the two?
In the cycling of them, the Martian simulant was a little grittier, so there was a little more difficulty in removing and replacing it first until, like I said, all the dust was knocked off. And then there was a very tiny, minuscule amount more simulant weight-wise that the plunger had taken on after testing. Very, very minimal.
Yeah, I mean, we're talking thousandths of a gram, right? Or what have you. So individual particles.
Very tiny. Yeah, not significant, I don't believe. Did they give you an idea of what tools to test? I mean, you had the hammer and the drill there. Those are pretty standard.
No, they didn't really give us an exact idea. So I kind of touched on that and the FEA analysis. So we're basically just going completely off of the customer requirements. And since they never disclosed what type of tools were going to be used, they made it challenging, but obviously we did our best. And I think I even noted at the end of the FEA portion that, hey, given the circumstances, it does meet the customer requirements. So it was a challenge, but no, we did not necessarily have an idea.
Yeah, I mean, just looking at the pictures and things that you see astronauts, like a drill is pretty common thing that they have. And so I just found the heaviest drill I could find and stuck it on there. The hammer being much lighter, we wanted to have a heavy object on the belt and then something not so heavy, just to sort of show that it can handle the weight.
Right. Yeah, that was perfect. Even on the extreme test, it didn't come out. So
yeah,
that was good.
Very interestingly, we didn't really have time to touch on this in the video really, but the way that it binds is ultimately, so whenever it goes, I don't know if you can see this, but it just goes straight in and out. It's very easy to take it in and out, but whenever it's weighted down, it binds up because of that moment. Kind of a happy accident, I guess, because of the clearances for dust. And when it's bound like that, it just will not, it will not come out of it. But when you're wearing it and you operate the tool, it comes out no problem because you just pull it right out, you know.
Very good. All right, we're still waiting for audience questions. While we're waiting, maybe tell us about your team name and your screen backgrounds there.
Take it away, Andrew.
Yeah. So our name is the Trailblazers. Blazar being a type of quasar or what have you that directs light at the observer, if I'm not mistaken. It's been a while since I've looked up that definition, but basically in a black hole or something emitting or ejecting material very, very quickly towards the observer, and it gives you this beam of light effect and the photos that the Hubble takes. So I just thought that was clever, and our university has never competed in this because our mechanical engineering program is only like 3 years old, I think. So Trailblazers, Trailblazer, thought that would thought that suited us pretty well.
That is perfect. Yeah, perfect. Okay, we've got some questions now. Can you think of a good application for this device on Earth?
Yeah, I think this could be, if we could get it to be a little cheaper. So it only costs us just a hair under 50. So it cost us about $250 each for these out of the 2 that we built. But if you were to buy 100 of them, which NASA probably would, you got like 8 on each belt, 10 astronauts or something, I don't know. 80 to 100 of them, it would only cost $50 a piece to make them. That's not the retail price, including profit or anything, but it costs about $50 a piece to make them. So I think we could make them out of carbon steel or something for Earth. It'd be way cheaper. And yeah, some type of utility belt here on Earth, I think it could be well suited for that application.
I think you see a lot of usage of utility belts in like the construction industry, especially carpentry work, which we happen to have a carpenter on our team, Trevor. So I think I think it would be fairly applicable to an industry such as that, where you have a hammer or something that you need to get and then get it out of the way and then be able to access it quick again. So something along those lines.
And having positive control, right? Because there's dropped tools. I've talked to people who've worked on field towers, like cell towers and stuff, and they said you will drop a tool eventually. Everybody does, apparently. So having positive control over your device, so to speak, I think, could increase safety as well.
Okay. And another question. So could the clearance for the simulant cause the device to become stuck, preventing removal of the tool?
Trevor, do you want to maybe?
I suppose it's possible, but since it's such a tight clearance, and as long as the ball is moving back and forth, the simulant has the ability to move around. So I suppose the answer would be yes, but it could be knocked out. And the way we tested it was pretty much the worst case scenario of if the entire tool was dropped into simulant. One of the things I was thinking about, and I wish we would be able to test it in the environment it would be in to see on average how simulant affects it. So although only 30% of the particles even had a chance of getting into that crack in between the sidewall and the plunger, like realistically it would be less than that because it wouldn't always be submerged.
Right. Only when the plunger is moving could anything get into it. So it's going to be static pretty much all the time. So particles are just not going to get in there. And I'll just be firmer and say, no, I don't think it's going to get stuck. Because, I mean, the clearance that we have on the rails is sufficient to allow the dust to move around a bit. We could have had it be like, whenever it slides in, it is perfect, very fine clearance, but then it would get stuck from the dust when you add dust to the equation. So it's loose enough and it's tracked right now, you can shake it around, that it's going to be a little harder. During the test, it was a little harder to remove the tool, maybe an extra pound or two of force, but it didn't get stuck. And I don't think it ever would get stuck, unless they did arms that day in the gym and they just couldn't pull it out of there.
Yeah. All right. Well, thank you, team. We are out of time, so appreciate your Q&A and good luck.
Thank you, Dr.
Thank
Irvin.
you.
Thank you.
Thank you.
All right. Our next team is from Texas State University, Team Aurora.
Hi, we are Team Aurora working on the dual-use wideband microphone array system. I'm the project manager, Hannah Louvier.
Hello, I'm Billy Flores.
Hello, I'm Jesus Hernandez.
Hi, I'm Daniel Lewis.
Hi, I'm Micah Snow.
Hi, and I'm Anthony Woods.
Our principal investigator is Dr. Richard Campo, and our NASA TSGC sponsor is Mr. George Salazar.
Our challenge was to design a dual-use wideband microphone array system.
As humans travel further into space, real-time communication with mission control on Earth will no longer be reliable.
Our system detects ultrasonic frequencies that are caused by pressure leaks and equipment failure and warns users of any hazardous conditions.
We also aim to provide a communication system for the crew members on board similar to a PA system.
As we combine these two systems into one, size, weight, and power are minimized, which is ideal with aerospace engineering.
We were tasked to create a design using MEMS microphones to transmit voice frequencies in the range of 200 Hz to 6 kHz, while simultaneously detecting ultrasonic frequencies greater than 20 kHz.
We'll use this signal generator to simulate an ultrasonic leak, and our system should activate a warning.
So let's talk about how we accomplished this.
This is our top-level block diagram. The dashed lines represent human speech, and the dotted lines represent the ultrasonic signals. Human speech and ultrasonic frequencies are simultaneously filtered to attenuate unwanted signals outside of their ranges. The system will pass human speech and emit a warning tone along with visually displaying the detection, direction, and intensity of an ultrasonic frequency. A challenge the team had was coming up with ways to test our system. So we started with two methods, with the leak simulator on the left and the frequency generator on the right. The leak simulator is designed to simulate air leaks at different pressures by adjusting the pressure regulator. And the frequency generator allows us to select ultrasonic frequencies and amplitudes for precise system testing. Unfortunately, the leak simulator predominantly produces audible leaks that are filtered by our system. The piezo speaker was mounted to a stand to prevent shorting. It is now our primary testing system.
The MEMS microphone array is 8 microphones and a one-dimensional circular array to show the sound localization capabilities of our system. The array is much larger than a flight-ready version would be to allow us to create and demonstrate the proof of concept. MEMS microphones are very small, and you could fit all 8 microphones on an array the size of a quarter. A Faraday cage throughout the assembly was made to protect the signal from the wires in the system behaving as antennas. Microphone 8's signal is used for both voice and ultrasonic functions.
This is the ultrasonic amplification and filtering system. The ultrasonic detection feature is made possible by two functions. First, the signals are received by the 8 microphone MEMS array. Each MEMS microphone will send a signal through its respective channel and then amplify to a detectable amplitude, which will set off the warning system. Second, the system filters all signals in each channel below the ultrasonic frequency range using 6th-order low-pass filters. The amplified and filtered signals through each channel are then output to the rectifier.
We're now at the ultrasonic rectification subsystem. The subsystem is made up of a half-wave rectifier that converts the alternating ultrasonic signal from Jesus' subsystem to a 0 to 1 volt varying DC voltage. The system can rectify different sinusoidal waves in the 20 kilohertz to 80 kilohertz range at varying amplitudes from 0 to 15 volts peak to peak, with an average voltage drop of 0.6 volts. A Zener diode clipping circuit was added to cap the output signal to 4.7 volts. This is to protect the warning subsystem Arduino analog input pins from exceeding its maximum rating of 5.5 volts.
We are now at the warning subsystem.
My subsystem receives input from the ultrasonic rectifiers and determines if an ultrasonic signal is present. When a source is detected, my subsystem outputs an auditory warning by sending a PWM signal with a frequency of 1 kHz to the audio output subsystem, and a visual warning by lighting an LED indicator. Both warnings scale based on the intensity of the signal. The auditory warning increases from 1 tone per second to 4, similar to a Geiger counter, and different colored LEDs are activated.
After receiving the signal from the warning subsystem, each microphone is updated on the GUI in real time. The visual display is comprised of a system status feature that notifies the user an ultrasonic leak was detected, a voice toggle switch to show if the voice communication feature is active, the signal intensity of all 8 microphones, and a sound localization feature that allows the system to detect and localize ultrasonic frequencies in a one-dimensional space. The localization feature of the GUI mimics the physical design of the array in the form of a circle. The signal intensity is represented by color, with red representing the highest intensity leak. This demonstration shows the functionality of the localization feature. As the microphone array is rotated, each microphone can read the ultrasonic signal and ultimately show which mic is experiencing the simulated frequency and the intensity of that signal.
The largest detection sensitivity of the system is around 24 kHz. At this frequency and of similar or greater magnitude, the detection range ranges from about 1 centimeter to 70 centimeters. Past this distance, the source leak would need to be of greater magnitude. To show the average detectable response for our system, the function generator is seen generating frequencies from 18.6 kHz to 44 kHz at the max range of 70 centimeters. The system can detect frequencies above this, though the source's magnitude would need to be significant.
The power supply subsystem uses one AC to DC converter that takes 120 volts AC from the environment and outputs plus or minus 15 volts. The voltage is then stepped down to give each subsystem its necessary voltage. The initial design used 2 converters, but to minimize the material and power used, only one supply was implemented. The applicable subsystems are receiving the appropriate amount of power while saving weight, which was a constraint for the project.
The voice channel receives input from microphone 8, then uses an amplifier with a 3.2 gain before cascading into a passive 6th order low-pass filter with a cutoff frequency of 6 kHz. The communication toggle switch is a feature of this subsystem, which allows for the voice signal to proceed to the audio mixer while simultaneously passing a 5-volt signal to the Raspberry Pi to activate the voice active indication on the display.
This is the audio output subsystem. The audio output subsystem receives the warning tone and the filtered analog voice signal, sums the 2 signals, and outputs to an off-the-shelf power amp speaker. The audio output subsystem has a potentiometer which allows for volume adjustment of the voice signal over the warning tone.
To use the voice function of our system, the user activates the communication toggle switch. The communication toggle switch is a double-pole, double-throw switch, which passes the voice signal to the audio mixer, as well as sends a voltage signal to the Raspberry Pi for the display. When the switch is activated, both the user interface and the red light on the LED will indicate that the microphone is live. The microphone used to pick up the sound is in mic 8 of our array and passes to the speaker. The volume knob can be turned from low to high. The analog mixer allows both voice and the warning tone to be heard through the system simultaneously. To silence the warning tone, hit the reset button. And to reset the system, press and hold the reset button for 3 seconds.
Some of the improvements we'd like to make with this system include advanced filtering. This would allow us to normalize the frequency response of the MEMS microphones in the upper range. Some of these upper range frequencies have a response beneath 0 dB, and honing in on those areas would allow us to better control the gain and increase the response in those areas. Another improvement we'd like to make is micronization of the entire system. So creating a custom PCB and using surface mount device would allow us to really minimize the space that we use and decrease overall weight. We'd also like to create better testing systems. It's kind of tricky to generate ultrasonic sounds and then also record them. So implementing some better systems to really verify that our system does what it's designed to do would be great. We'd also like to implement our system into a specific environment. This would really allow us to see where the system is strong and where it's weak. So improving on those areas would be very beneficial. We'd also like to implement a database that could log ultrasonic detections over time, and then using that recorded data, make improvements to software so that it's more dynamic in nature. And lastly, when you're floating around in space, you don't want to use a hardware switch to turn your microphone on and off. So we'd like to implement some voice control into the system.
Thank you so much to NASA TSGC for this opportunity to work on the project. Also, thank you to Dr. Richard Campo and Mr. George Salazar for all of their endless advice and support throughout this process. And also thank you to Texas State faculty for consulting us when we needed help. We will now take any questions that you might have.
Okay, welcome Team Aurora.
How are you doing today?
It's going well. So audience, please ask your questions at slido.com, enter the code TSGC, and you can view and upvote any questions for the team. So let me ask, just to start off this time, so what were your biggest challenges this semester? I mean, we've had COVID, we've had the winter storm. What else?
I think there's probably two answers to that question. The first is one we've come up with a couple times is how do you present a audio project without people's actual ears being able to hear it? Much less like a ultrasonic project that, you know, people can't even hear ultrasonic signals normally. So that part was answered in the work that we did and creating the ultrasonic detector. But even in showing, you know, we could have easily voiced over things. So we just decided to show the speaker actually outputting and doing that recording for it. And then the other, I mean, definitely had many different design challenges as we went and kind of choosing which things we wanted to try to improve the system and which things we just kind of had to accept as limitations and move forward from there. And if any of my teammates wanted to elaborate on that.
Like mentioned in the video earlier, one of the other big challenges that we had was developing, I guess, proper testing procedures or being able to test our system in that ultrasonic range. A lot of the speakers, we ended up using a piezo speaker, but a lot of those types of speakers that can produce those ultrasonic frequencies that we're looking for, some of the nicer ones ended up being a little too expensive to implement into our project. So that was another big challenge, to be able to find components and speakers and devices to be able to test our system.
Yeah, we definitely couldn't afford a SPL meter that measured an ultrasonic range either. We worked with one that went up to 20 kilohertz, but we kind of just had to make some logical assumptions based on what we measured in the audible range from there.
Yeah, in terms of hardware, I thought your leak detector was a very good idea. I guess, did you get some ultrasonic signal out of that or not?
Out of the leak simulator, we were able to get some ultrasonic signals from it. Unfortunately, the leak simulator had to be a little too close to the microphones to be able to pick up those leaks. From our overall project, I think working on those the frequency bands that dip below 0 dB and normalizing that, I think would really help us out to actually be able to use the leak simulator and test our system. So.
Okay, good. We're getting some questions now from the audience. So what are some of the methods to implement this outside of the space station?
I can take this one. Some of the things that we discussed as a team is definitely being applications that you could use beyond space station, or the Orion capsule would be any sort of environment where there's pressurized, fluids or gases that could pose a threat to the safety of people if there were some sort of leak. So this is any sort of like chemical or natural gas processing plant that currently rely on using handheld detectors to search for leaks. This would enable them to kind of have a more general idea of what how their equipment is currently functioning and any issues that might be arising.
Yeah, and to add to that, the array that we made was one-dimensional on a 360-degree plane, but really the MEMS microphones are very small, and they could be arranged around any kind of area. If you were expecting to monitor a leak in maybe a certain joint with a pipe or a certain area of the space station, you could design the array for that specific environment. And even though one of the findings that we have is our range is very limited, but if you know where you're trying to target that leak for, you could really make that design decision from the very beginning and just target the microphones towards that area.
So were you specifically looking at Orion capsule or station or not?
No, we kept it general for any kind of environment. We didn't want to design it specifically to one thing. Like we said, we chose to do the one-dimensional array just to show that sound localization was possible. And at a certain point, as we mentioned in our expansion, this system really could be expanded to be 400 microphones, however many that you needed to monitor your area. And even just doing 8 was a big challenge for us. And there was a lot of physical hardware since we had to scale everything up so that we could solder ourselves and use that. So we didn't pick a specific environment to monitor like that, but I think our findings show that they could really be applicable to any environment.
Okay, next question. Speaking of other environments, did you look at how the Navy does it on their subs? I know that they have this problem as well.
We didn't actually do much research into how the Navy does it. I know that there are some different methods. I'm not sure if they're using any kind of digital approach. One of the things we did decide to do was use a completely analog signal for our system. So any system is going to have its limitations, and I'm sure that whatever system they are using on the submarines probably has similar limitations or trade-offs that they had to decide whenever they were designing it.
Okay, and then I guess speaking about the trade-offs, so you've got the PA system as well as the leak detection. Were there any trade-offs that you had to do to make those work together?
Absolutely. Jesus, do you want to talk about the audio output at all? Not to put you on the spot.
No, yeah, of course. Definitely one of the trade-offs was having to establish that distance between our audio output subsystem and the microarray itself, because it does because our microarray does pick up between the 200 to 6 kilohertz. Our audio output subsystem did need to be in a separate room, so that way there wasn't that feedback draw. So that was something that we had to compensate for, and also ensure that the audio output system was not louder than it needed to be, so that way it wasn't picked up by the microarray.
Additionally, too, I was initially using a bandpass filter for the voice, and since our environment didn't really have any low-end interference at all, we decided to focus solely on the upper range and just did a low-pass filter at 6 kilohertz to get rid of all of the ultrasonic interference in the microphone.
Okay, and then say, for example, you were going to install this in the Orion capsule. What would you start looking for in order to figure out where to place all your components?
Well, I guess for me, the first step would be to look to see where spacecraft have had leak issues in the past, where things are under immense pressure. Mechanical side of things isn't really my specialty, but certainly getting with those kinds of people and finding out where the vulnerabilities of the system may lie. We also talked about one of the expansions that we could possibly do would be creating somewhat more of a handheld device or something like the one that we created that could be placed somewhere, or at least temporarily located somewhere. So I know that they did have a leak in the International Space Station and they had to hunt for it manually. And since the leaks are so small, it takes quite a while to do that. But that would be my first guess, is to look for where the vulnerabilities already exist and place your microphones close to there. I don't know if anybody else wanted to add their thoughts.
Yeah, I can speak on top of that too. I think a good thing to consider would probably be the best placement possible so that it could also benefit the astronauts in terms of using or placing it in an area to where they can interact with this overall system just in the same way that they do with the rest of the systems that are on the aircraft. So centrally locating it so that it's not out of the way and they're not having to go into a certain area to actually read where the sound localization is happening.
Okay.
Yeah, and we also mentioned definitely being hands-free. You don't want to have to push a button in an emergency to be able to be heard, but maybe having some kind of voice, you know, kind of like your Alexa or something like that at home that you could say, hey, I want to talk to whatever room now would be really beneficial.
All right, great. All right, thank you, Team Aurora.
Thank you, Dr. Urban.
Yes, thank you.
Thank you, sir.
Thank you.
Thank you.
Our next team from the University of Texas at Tyler is team HEC 28.
This is team HEC 28. The title of our project is to design an integrated protein exchange membrane fuel cell system. Next. My name is Daniel Jordan.
Oscar Palencia.
Marco Ponce.
Rowan Rizal.
Ormo.
This is team HEC 28. The title of our project is to design an integrated protein exchange membrane fuel cell system. Next. My name is Daniel Jordan.
Oscar Palencia.
Marco Ponce.
Rowan Rizal.
Ormo.
The purpose of this project is to model and simulate the balance of plant for a regenerative fuel cell system that can serve as a backup energy source in lunar environment. Next. NASA has continuously looked for ways to develop an effective power generation system that can provide sustainable energy to meet its challenging environmental conditions in lunar space. One device that NASA has implemented is the fuel cell. Unlike batteries, which runs out over usage, fuel cell produces clean, hazardous-free, constant power. It produces electricity through an electrochemical process between hydrogen fuel and oxygen to produce water and heat as a byproduct. Theoretically, the efficiency of the fuel cell is 83%, while the power needed for one lunar cycle is 100 watts. The design is a self-contained unit that can be transported to the lunar space, where it can be powered on by a photovoltaic cell during lunar day. Since the project is meant for lunar exploration, our design was modeled under Earth-based conditions. By doing this, we were able to replicate the design by using simulation to show performance of the whole system through the in-lab testing of the anode side to generate a power of 100 watts. Next. This animation shows how hydrogen flows into the fuel cell through the anode side and oxygen through the cathode side. The hydrogen ions flows across the membrane towards the cathode, while the electron flows through an external cycle, does work, and returns back into the fuel cell. The oxygen from the cathode recombines with the incoming electron and hydrogen ion to produce water and heat as a byproduct. Next. It is regenerative because the electricity produced using water from the fuel cell to produce oxygen and hydrogen by way of the electrolyzer, which is then recycled back into the fuel cell for continuous flow of power. Next.
Here is our project objectives. Last semester, we focused on design, which is to create the balance of plant for the fuel cell system. This semester, we focus on the simulation and testing. Simulation in the operation of the balance of plant as to see the relationship between various components. And the testing is to build and test an anode site using earth-based conditions as to give a physical representation of the system. And the last objective is the power, to deliver a net power within 100 watts as the value was set forth as a requirement for the project. Here we have the specification table. The simulation models were using the fuel cell and the electrolyzer from these two brands, which is Infinity and Sustainable Innovations. For the fuel cell, it had a number of cells of 7 with an active area of 150 centimeters square. For the electrolyzer, the number of cells was 5 with an active area of 80 centimeters square. Simulation enables experimentation on a valid digital representation of a system. The simulation are key to see if the values are reasonable and acceptable for the project.
This is our Simulink design schematic. At number 1 is a PEM fuel cell, which will convert the chemical energy of hydrogen and oxygen into electricity through chemical reaction. Number 2 shows the electrolyzer, which breaks down water into hydrogen and oxygen. Number 3 shows the hydrogen and oxygen entering the fuel cell through the anode side and cathode sides respectively. And the number 4 is a water storage tank, which holds the fuel cell byproduct, which is water. And for the thermal fluid management, we have a cooling line, which will use DI water, heat exchangers, and dehumidifiers. And there's also supporting components such as pumps and compressors. The Simulink modeling and simulation the team conducted will focus mainly on the fuel cell, electrolyzer, storage tanks, pumps, and compressors. Next.
Our model was based on a 24-hour cycle with the fuel cell operating for the first 12 hours. A small time sample is simulated to show the zero initial condition, transient, and steady state of the fuel cell. The fuel cell subsystem was modeled with the current being the input and the mass flow rates of the gases and water being the outputs. Next. For the last 12 hours of the 24-hour cycle, the electrolyzer is in use. The small time sample shows the dynamic behavior of the electrolyzer from its zero initial condition, transient, and steady state. Much like the fuel cell, the electrolyzer was also modeled using the current as the input and the mass flow rates of the water and gases being the output. However, since the fuel cell consisted of 7 cells and the electrolyzer of 5 cells, the electrolyzer had to be adjusted to match the mass flow rates of the fuel cell, which we use for our BOP components. Next. The H2 and O2 storage tanks were simulated for a complete 24 hours. They were modeled using the ideal gas law. For the first 12 hours, the pressure and moles of the gases are depleting. This is due to the fuel cell using the gas as fuel in the chemical reaction that produces a power output. For the last 12 hours, the pressure and moles of the gases are increasing. This is because the electrolyzer is in use. This time period is also known as the recharging phase. Next. For the water storage tank dynamics, the opposite behavior is observed in comparison to the gas tanks. A positive slope is observed for the first 12 hours because the water is being produced as product of the chemical reaction taking place in the fuel cell. The electrolyzer then uses the water for the last 12 hours to break down hydrogen and oxygen back into its gas states. Next. The results show that both temperature and pressure influenced the fuel cell's efficiency, which also affected the round-trip efficiency of the RFC system. 3 cases were simulated where only the fuel cell's operating conditions differentiated and the data recorded. Next. For the 3 cases, the temperatures were changed and the pressure ratios were also changed, which yielded 3 different round-trip efficiencies. The fuel cell generated 174 watts. The pump consumed 0.02 watts. The compressors consumed 13 watts. And the electrolyzer consumed 378 watts, which was provided by the solar panels. In terms of power in and power out, the power efficiency was 44%.
Here we have the in-lab testing. As mentioned before, the testing was using earth-based conditions. The setup was evolving due to improvements throughout the semester. The complexity also grew due to add-ons done to the system. The arrangement of the components was important to easily locate errors, but as well as to keep everything compact to minimize space.
The figure shows the layout of the lab setup of the equipment to run the fuel cell in the earth-based condition. The system starts from the hydrogen generator, which supplies hydrogen to the fuel cell, produced from the electrolysis of the distilled water. The hydrogen is then passed to the mass flow controller, where we control the flow rate, and to the pressure transmitter, which controls the pressure. After that, hydrogen goes to the fuel cell through the supply valve. The blower attached to the fuel cell will provide the oxygen and also cool the fuel cell. The water and the excess hydrogen are forced out through the pores wall, the voltage and the current from the reaction in the fuel cell is measured using DC electronic load device. Next. The fuel cell tested in the lab was S100 by Horizon brand with 20 cells and power output of 100 watts. The operating temperature for this fuel cell was around 25 degrees centigrade and the pressure between 21 to 22 psi. The hydrogen generator was QL1000 by Fuel Cell Store, which produced 99% pure hydrogen at the flow rate between 0 to 1 liter per minute and the pressure between 30 to 60 psi. The AC voltage of 110 to 220 volts was supplied to run this generator. Next. Figure shows the electrical diagram of the tested system. Arduino microcontroller was used to control the blower and the valves, whereas NI USB data acquisition device was used to measure and record the flow rate, pressure, and the temperature of the hydrogen supplied to the fuel cell. Next. Data was collected and recorded using the LabVIEW. Figure shows the front panel of the testing, which includes the control for the blower and valves and the measurement for the temperature, pressure, flow rate, voltage, current, and the power. Next. Here is the videos which shows the quick demo of the experiment. The generator is producing hydrogen at the given flow rate, which passes through the flow meter that will adjust the flow and pressure going to the fuel cell. The output voltage and the current from this fuel cell will be measured using NIDC electronic load and in the LabVIEW front panel. The factors that affected the testing results were pressure, flow rate, temperature, and the time of the operation. The optimal performance was obtained at 8 psi and 1.023 standard liter per minute and 23 degrees centigrade, which was around 80 watts, operating at 14.5 volts and 5.5 amps. Next.
One of the feature improvements that the team had was to maintain steady flow rate. The optimal performance was rated at 1.4 standard liters per minute. However, the flow rate was capped at 1 SLPM by the flow meter specifications. Next. In conclusion, theoretical analysis and calculations were performed to confirm the effectiveness of the design. Simulink was used to model and simulate the BOP under lunar conditions. Then, anode-side testing was conducted using Earth-based conditions. This is important because to see how a similar system to our design schematic would do in a real-world scenario. The pressure and flow rate had the greatest influence on both the simulated and in-lab testing results. By completing this project, the team could understand the importance of a balance of plant and how it affects the efficiency of a system. Next. The team would like to acknowledge the following UT Tyler faculty members, former team member, and finally TSGC, who are our project collaborators and sponsors. Thank you for watching our Design Challenge Showcase, and we'd like to open the next few minutes for questions.
Okay, welcome Team HEC 28. Audience, please submit your questions using slido.com. Use the code TSGC to ask your questions for the team. And I believe everyone's online here. All right, good. So how did it go, team? What were your biggest challenges this semester?
Yeah, sir.
I think the biggest challenges this semester was actually getting the fuel cell and the whole setup running and actually acquiring some data. Initially, whenever we went to the lab, we had to fix the fuel cell because the previous team last year had burned the fan. So we had to buy a new fan and get the fuel cell to run. And also we had to figure out the generator. The generator was throwing some sparks, so we had to figure why it was doing that, and also just learning the whole setup and running new programs that we hadn't used before. Anybody else?
Yeah, I would say like we were doing some electrical stuff that were pretty new for us, like for mechanical, doing the electrical stuff was new, and it was a good experience. And we worked a lot on LabVIEW for the data collections, and basically, yeah, the setup was doing the setup for the lab for the testing was kind of challenging for us for this semester.
Okay, good. So speaking of the whole system, so you're dealing with hydrogen. What are your safety precautions that you need to take?
So for the hydrogen generator, like we use distilled water, and for the safety, we attach the gas sensor in our controller, so we can detect any leakage from the hydrogen. So, and also we are operating this hydrogen at low pressure, around 7 to 8 psig, so it won't be that much harmful. But of course, like we have to use a hydrogen sensor for detecting the hydrogen, like the leakage in any systems.
Good, good. So with your whole system, are there terrestrial applications that you would really recommend?
Yeah, we did that on the terrestrial applications, like on the earth-based conditions, because we were trying to see the results, like if we operate at different conditions, because for the lunar application we had different operating conditions, and we were just going to observe the results, and then do the further analysis for that, how it's going to affect if we run the actual system in the moon.
Okay, and what are your next steps to actually assemble the entire system where it might be commercially viable?
Repeat that again, sir.
Can you repeat that one more time? I didn't.
So you have all your components, but if you wanted to assemble it into one unit, what would it take to put that all together and make it commercially viable?
I think the cathode side, we'll have to build the cathode side to have a complete system, because in the lab, in the in-lab testing, we only built the anode side. And then our model, we actually use pure oxygen, and in the in-lab testing, we use the air. So we would have to, probably do more studies and actually build a system where pure oxygen, where we use pure oxygen.
Yeah, also I would say, like, we have to change our fuel system. Right now we are using a hydrogen generator, but like for the actual system, we'll be using the pure tanks, hydrogen tanks and the oxygen tanks to supply the fuel for the fuel cell. And we might have need to make adjustments on the components, like different components we use. So that would be the thing for the commercial.
We also like to work on the cooling system of the fuel cell, so that we can be able to regulate the temperature and also the power is coming to the fuel cell from the extreme heat exchanger.
Okay, great. I don't see any more questions here. So I will say thank you, team, very much for your work.
Thank you very much.
Thank you very much, Tim.
And that concludes session 2. We will take a 10-minute break and be back at 3:45. Thank you.
Okay.
Good afternoon and welcome back to session 3 of the Texas Space Grant Consortium's Design Challenge Showcase. Our session 3 begins right now at 3:45, and we have 3 more teams this afternoon. Tomorrow, starting at noon, we have another set of 10 teams. So please join us either online at YouTube, or students join us here on the webinar tomorrow. So first up this afternoon, University of North Texas Denton Space Eagles with the private cloud with wireless Internet of Things.
Hi, welcome to our presentation. We are Denton Space Eagles and we are here to present our private cloud with IoT. First, we'll start with introductions. I'm Mark Yonker.
I'm Shangda Li.
I'm Micah Warren.
I'm Yichen Feng.
And I'm Ricardo Garza. And I would like to introduce our project. With NASA periodically sampling sensors for different kinds of use, collection and analysis of the data is becoming more difficult due to the high latency over the connection to Earth. With the wide variety and accessibility of different IoT platforms that can collect and analyze sensor data, there is an opportunity to eliminate high latency problems with one of these IoT platforms. Our objective is to examine an open source IoT private cloud platform and to examine its functionality aboard a spacecraft without a connection to Earth, as well as have test applications to see how the platform would process and handle the data. All the data should be stored aboard the spacecraft with only relevant data being sent to Earth. We will next give a brief overview of our implementation.
For the IoT cloud platform, we have chosen to use ThingsBoard. To communicate with ThingsBoard devices, utilize HTTP. Telemetry data from the devices is processed through ThingsBoard. Based on received telemetry, if a defined threshold is broken, an alarm is sent out. We developed 4 different test applications to evaluate ThingsBoard's capabilities. Let's start with my application first. The field monitor monitors real-time air pressure, temperature, and the fuel level inside the fuel tank. It has an alert for dangerous fuel status, like high air pressure, high temperature, or running out of fuel. In addition, it can calculate the remaining flight time and distance according to the fuel burning rate and the speed of the spacecraft.
So the health monitor test application is a biometrical data tracker. It tracks the heart rate and SpO2 saturation level of the user, and then the server side will receive the real-time data from the application and update them. The application also comes with a microphone and speaker for communications. An alarm on server side will be raised once the abnormal data present.
The third test application is a weather station. It uses an anemometer, a wind vane, and a rain gauge for measuring rainfall, wind speed, and wind direction. It has a sensor for measuring temperature, humidity, and air pressure. When certain conditions are met, ThingsBoard will send out an alert.
Our fourth application will be a motion sensor camera. Motion sensing has a wide range of uses, from automatic doors to floodlights outside your house. We've decided to use it to record any motion detected by a PIR sensor and ultrasonic sensor. Using both in tandem increases accuracy and gives extra data like the distance the object was at. When motion is sensed, the camera is activated and will record and then upload the footage to the cloud. In the cloud, recorded footage will be run through machine learning algorithms using Image AI and perform object detection on the video. Image AI is an open-source Python library with self-contained deep learning capabilities. Once processed, the video will be displayed in the cloud and sent back to the edge to be displayed there as well.
The IoT cloud platform that we chose, ThingsBoard, has the ability to communicate over several different protocols: HTTP, MQTT, and Bluetooth Low Energy. On HTTP and MQTT, they can communicate over secure means, so the data inside will not be intercepted or modified. Once received, ThingsBoard can then process the telemetry from the devices in several different ways, from simple offsets to using other data together to formulate something more complex. It can also analyze that data and send an alert if a threshold is broken. Alerts can be sent through emails, on the dashboards, or send an HTTP packet to another device where it can handle the alert in its own way. And all of this can be done without an internet connection. As you can see here, we have some of our devices sending data to our dashboard that end users can watch. We can go to the rule chains and see the rule chain that starts filtering out all the main data. Some of this is provided already by ThingsBoard for simple operation. And to the right is the stuff that we created so that way the different applications can process their data. Here we can open up Applications 1 rule chain and see the different things that were implemented so that way it can process its data. If we go back to the root rule chain, we can see that many of the different applications have their own rule chain so that way they can process the data the way that they need to and perform any type of actions like sending alarms and alerts to users if needed. For future work, teams that continue to work with ThingsBoard, we would suggest looking at implementing third-party analytics, maybe adding GPS on some vehicles and using ThingsBoard's maps for tracking, and even looking into the remote management of devices through ThingsBoard like a smart meter. For teams working on another platform, we would suggest looking at what we've done and comparing it to how ThingsBoard operates.
ThingsBoard's provided rule engine is great for operating on integer, float, or string telemetry. Comparatively, ThingsBoard's support of operating with other types of telemetry force-fed. ThingsBoard allowing development of custom rule nodes helps them, as well as ThingsBoard allowing development of custom dashboard cards.
We would like to thank everyone on this list for helping us on the project and helping coordinate this event. Thank you very much. Here are the references that we used. Thank you for watching.
Okay, welcome Denton Space Eagles.
Good afternoon.
Hello. Thanks for having us.
Absolutely. So audience, go ahead and submit your questions on slido.com. Use the code TSGC. You'll be able to view and upvote other people's questions. So let me ask you what we've been asking every team. What were your biggest challenges this semester amid COVID, the winter storm, and the project?
I know for me personally, I run a different schedule from everybody. I work at night, so I usually have to go to sleep around 6 in the afternoon and wake up at 1 in the morning, go to work. And so I run a completely different schedule from everybody, and it gets kind of hard communicating with them sometimes because I'll be up, and if it gets slow, I'll work on the project a little bit, but they'll be asleep, and I'm just here.
By the time everybody else gets the energy to work on it, it's about 6 p.m. right when he's ready to pass out.
Oh, yeah.
We have to keep him up past his bedtime sometimes.
Yes, we've kept him up past his bedtime many times.
For me personally, the hardest thing was definitely doing a lot of the work on the hardware from the PCB to the enclosure, because a lot of the tools you need to make those, we don't have in our personal homes, like the CNC machine that would be up at the workshop up at the university, and getting all that done can be difficult in the times that we're in right now.
For me, it's my challenge was to actually implement the biometric sensor for my application, because the original sensor I ordered was actually used for Arduino, but we are using Raspberry Pi. So in order to solve that problem, I tried to write another drive program by referencing the original drive program for Arduino. But the original drive program, it's written in C, and the sensor is very unique. It has a very unique initiation progress. So the driver program I wrote for Raspberry Pi couldn't make the sensor to run. So I later have to replace it with another sensor.
And for me, I think I have two challenges on my application. One is PCB design. We build a customer PCB for our applications. And then another one is doing computation on the cloud side. Since I need to calculate the speed of spacecraft, so there's no sensors I can sense speed directly. I have to use the accelerator to sense accelerations and use them to calculate the speed. So a lot of calculation have to done on the cloud side. Yeah, that's my biggest challenges. That's it.
For me, trying to provide, as the one that was working on the server a lot, trying to find ways so that way we could all work, like Shangda was talking about, the rule chains, so that way they could work on the rule chains and sending telemetry remotely. We tried to use a VPN, but the version of Linux that the Raspberry Pis use did not mix very well with the open VPN software that we were trying to use. So it did prevent some interesting challenges.
Okay, very good. Thank you. So audience, please ask your questions at slido.com. Use the code TSGC. We're still waiting for a few questions. I guess I'll go through mine. So how did you figure out what test applications you wanted to go through? The fuel, the health, the weather, and the motion?
Each, you can go ahead.
You can first.
Okay, so each of us kind of just were like, okay, we need to make an application that stresses the cloud computing in some way. So we thought, what kind of data can we send that would, stress it? So we thought of a lot of computations and also the video and audio and, the motion sensor camera. I don't know how everybody exactly came up with their specific application, whether it was just Googling around trying to find something that would be interesting or not, but I came up with it pretty early.
Good, good. So then how did you decide on just 4, and how expandable is your system?
I'll take that. Thingsboard is one, it's an open source platform. So within its capabilities, you could add to it somewhat, but mostly the software is not the limiting factor. It is going to be the hardware that limits like how many applications you can do, and how many are sending messages at the same time, how many remote users are you going to have viewing data. There's different ways that you could implement it so that way it speeds up, if you have a system with more RAM in it. But we weren't really trying to do that too much. So we really wanted just a variety of different things. You can always spend more money and get better hardware pretty much. So we didn't really go for testing that.
Understood. Yes. Yeah. You just wanted to demonstrate the product. So if you put it in, say, a space station, what are the different types of applications that you could see it doing, working with?
I think it could work with Team Lit, the other University of North Texas team. Their stuff we had almost thought about at the beginning. It's like, oh, it'd be almost kind of interesting to see how their stuff integrated with ThingsBoard. Due to the time pressure and such, we never really even explored trying to do that. But there's so many different things, and several different of the applications we've seen today from other teams could just be integrated through ThingsBoard, and then you don't have to worry about as much of a user interface because most of that's going to be provided to you.
Okay, and how did you find ThingsBoard? I'm not familiar with that until you presented it today.
Do you get this, Ricardo? Or
No, you got it.
Okay. Mostly what we were doing is we saw the last year's UNT team that did this project, and we wanted to see what we could do to expound upon it because they had used ThingsBoard as well. We read like their conclusions and kind of the work that they did, and we wanted to take it and push ThingsBoard more to its limits to see if it's actually going to be a good product to use for NASA.
Okay, that's right. Yeah, I do remember last year they did use it a little bit. And as you said, you pushed it to the limits now. So
Yes.
Did that team help you or advise you at all?
Only through their text and the stuff that they submitted. We did not have communication. Yeah.
Yeah.
All right, good. What else are your takeaways from this semester?
It's been very interesting. Everybody having to work together. And then I know the other day we finally came together after a long time and everything went wrong.
Yeah. As our professor
Yeah.
said, like whenever you get together and put it all together, it's not going to work. And it didn't for a little bit, but we spent about a day or two working on it just to fix it so we can continue integrating and working on it.
That's good. So you were able to meet in person to put this together?
Yeah, for a few hours actually. Everybody wearing masks and everything. We were trying to make sure everything was interconnected and would actually work. Send data back and forth, and the first couple hours, yeah, that wasn't happening.
Yeah, due to the VPNs not working on the Raspberry Pis, that their code was running great on their own devices, but once we tried to integrate ThingsBoard into it, then all of a sudden, we were getting errors where there shouldn't be an error or something like that, just due to them not being able to test it because of the remote nature of what we were doing.
Yeah, you would think your project over all the others would be able to work remotely, but really putting it together was the final test. Very good, very good. Well, thank you very much, Denton Space Eagles.
Thank you.
Thank you.
Thank you for having us.
Thank you.
Okay, our next team is from San Jacinto College and is Team ACT, ACT, and they have been working on machine learning audio denoising. Again, while the video is going, audience, if you could go to slido.com, enter your questions into that system, use the code TSGC to have access to all the questions. You can ask a question or upvote other people's questions.
Good afternoon. My name is Pamela Betts. I'm a computer science professor at San Jacinto College, and this is Team ACT. Their project is TDC number 71 for spring semester 2021, and it is machine learning audio denoising. I'm going to let the team introduce themselves and then present their project. Thank you.
Hello, I am Joe Patrick Perlera. I'm currently a student at San Jacinto College. I am majoring in biology. I have a background in video editing and thus deal with the issue of needing clean audio. This makes the promise of machine learning, cleaning up audio, a very promising prospect to me.
Hi, I'm Alvaro. I am a major in computer science. I'm interested in this project because of the machine learning.
I'm Brian Scott. I am in my sophomore year of San Jac, and I am majoring in computer sciences. I just loved anything to do with space and NASA, so this project was kind of just drawn to me.
My name is Julio Buenrostro. I am a sophomore in San Jac. The interest in the project is that it's something that I haven't done in my career of doing programming, and it's something that I'm really looking forward to.
Hello, my name is Shane Martin. I am majoring in electrical engineering. I'm a sophomore in San Jac. My interest in the project is to learn about machine learning and taking that knowledge and into robotics.
I'm Julio Buenrostro, and I'm showing our project introduction. Our project has to do with machine learning audio denoising. We plan to show that NASA can pre-process audio using machine learning to remove any acoustic interface and denoise audio as well, without the help of any major cloud servers, so it can work properly offline. Our purpose is to show that the audio can work as a portable software system to help us with real-time denoising as well.
Hi, I'm Alvaro, and the desired deliverables or objectives of the project are to make a front-end offline system that is capable of real-time denoising and playback denoise audio, as well as including a description of the hardware and software of the elements we use, along with instructions on how to use the system. At minimum, we are creating a system that denoises audio and saves it in new files. The playback and the real-time operation are stretch goals.
Hello, I am Joe Patrick, and I'll go over the materials and methods our team used. The materials that we used are Python Free, sklearn, Raspberry Pi, TensorFlow, NVIDIA Jetson Nano Developer Kits, Audacity, and Pi Audio Analysis, which is licensed under an Apache License 2.0. The methods that we used are to first use an algorithm to segment the unprocessed audio into more manageable pieces that can serve as data points to train our neural network. The neural network was trained to denoise audio provided to it into clean samples. Once the neural network was trained, it resulted in an algorithm that would have offline functionality and be able to successfully denoise audio.
The results we earned from this project were we were able to run Pi Audio Analysis, which is a Python analysis library that meets NASA offline processing without the use of massive cloud servers. We're also able to supply audio by using Python. Long files may have too many artifacts that become a proper data point. Number and size of dead spaces produce meaningless training data. Slice longer audio samples into multiple 3-minute samples without dead space. Increase the size of data set for training the algorithm. We were able to clear audio using Audacity to show that we could manually denoise the audio, control to compare with the machine learning denoising algorithm.
Hello, my name is Shane Martin. We wanted to use machine learning to pre-process audio samples that denoise and remove acoustic interference. We also wanted to take training algorithms that could be loaded onto a offline system in real-time denoising. We were able to show individual elements that were possible. In addition, data and programs runs to get more data points for proper analysis. We use Pi Audio Analysis, which is currently using sklearn for training, but we want to change that to TensorFlow. In our future research, we want to demonstrate the difference between sklearn and TensorFlow to get an accurate audio denoising result.
The challenges our team faced while working on this project include a lack of experience with programming in Python Free, as well as machine learning, extraordinary circumstances such as the winter storm that devastated the state of Texas and left some team members members with broken pipes, coordination complications due to COVID restrictions, as well as team members being personally affected by the coronavirus, and finally the need of our target computer hardware needing to be appropriated. Here are the sources that were referenced by the team for this project. Our team also consulted with our NASA mentor and were informed that the Python library's Apache 2.0 open source license was acceptable for NASA purposes. Most of all, we would like to humbly acknowledge the people who helped us make this project possible. Our NASA mentor, Arjun, who was ready to guide us in the right direction, James, who was instrumental in helping us learn how to develop our programming skills, Dr. Roger Watkins, who helped us behind the scenes in matters that our team could not handle, and last but not least, Professor Betts, who poured her heart in helping us throughout this project and keeping the team from losing sight of the goal with her kind encouragement. She helped us all through the rough of times. Thank you for your time.
Okay, welcome Team ACT.
How's it going?
Going well. So let's start with your name. Who came up with the name and what does it stand for?
I think Brian was the one who came up with the name Team ACT.
We can't hear you, Brian. And what does it stand for? Can somebody else speak to that?
Team ACT, ACT stands for a computer team.
A computer team. Okay, very good. And how about your team patch design? I read a little bit about that. It looked really interesting. So that's a dragon silhouette on the inside?
Yes.
Okay, how did you come up with that?
We all took our time to, can you hear me now?
Yes.
Okay, we all came up with the design, submitted it, and we just kind of voted on which one we liked the best, which one was most fitting for us. And due to school mascot, we like to keep it all, with Sanjay.
Okay, perfect, perfect. So I looked at your bios. You're all different majors, almost. So how was that teamwork wise, trying to work together with people in different majors?
It had its difficulties because we all have a different way of thinking coming at this. Me coming from the computer science, same with Alvaro, we kind of had a gist and an idea of what we're getting into with the coding and that side of it. But everyone pretty much had a perfect spot on our team and was able to knock out every task that was given to them.
All right, very good. All right, we've got a question now. First question is, did you consider reverb effects on speech as well as background noise?
We were kind of just focusing on space acoustics and just noises from a normal, spacesuit, the thing that comes with all different types of audio interference. And we're working off of the audio samples that were giving to us. And we just recently got a little bit more audio samples that we can give to our learning system and teach it to cut out all that. So eventually we will be able to teach it with the reverb as well.
Very good. Yeah, I understand you were trying to get your audio samples for a while. What samples did you get from? Is it emission control or can you not talk about it?
We can't talk about it, but it was pretty cool to hear it.
That's what I suspected. All right, excellent. Oh, here's a good question. Can this be used for everyday audio conferencing?
The code that we used will be able to use, you can teach the machine to denoise whatever interference is there. So once it's fine-tuned, you should be able to use it with everything.
Yeah, the machine learning process itself is very versatile and can be used for, video conferencing if given enough video conference audio samples to be trained on. But the specific algorithm that we are presenting, it's, highly tailored to only certain types of audio, so it cannot be used for conferencing. But machine learning is very versatile. It can be trained on video conferencing audio and used for that purpose.
Okay, good. And then a related question here. How much delay is there in the audio denoising system?
Right now, we haven't really came across too much of a delay. I don't want to give too much information when we don't have exact amount because they've all differed. But we have cut down audio samples down to 3-minute segments, and we've been working with that and successfully been able to denoise it fairly quickly.
So you're talking almost real time or the time of the sample?
Real time is the goal, but at the time of the sample.
Okay. All right. And this is offline, correct? It doesn't have any internet connection?
Yes, this is offline.
Very good. All right. Next question. Has there been prior research in this area that you used to set your design goals?
We all did research into denoising Audacity Pi audio library. And we were able to kind of look at everyone's information and kind of piece together what we took from each resource that we had. So yes, but it's fine tuning what every good piece from everything we've researched.
Okay. And in your video, you already had a slide about all your challenges. Is there anything you would want to add to that in terms of challenges this semester?
Besides scheduling, we all have different schedules. I run a restaurant down in Galveston, and everyone else is doing everything that they do. COVID got to us, as everyone. The weather affected us as well, but we were all able to, manage through all of our challenges, figure it out. We were all able to meet online, even if it was at different times. I mean, I just went on my honeymoon and I was able to record what I needed to for our poster and video out there as well. So, challenges are meant to be overcome.
We also took, this project was supposed to be 2 semesters, and we brought it down to 1 semester. So that was a big challenge for us also.
Okay, great. What are your final steps that you need to do to complete this project this semester?
We need to take all these new audio samples that we just received, and we're going to cut them down, and then we're going to push them through for the machine learning just so they can try and denoise it. So by the end of the semester, hopefully we can compact it down and be able to finish it. But given the time restraints and some challenges, we should be able to get it done.
Well, good luck, and thank you, Team ACT.
Thank you very much.
Thank you.
Thanks.
All right, our next team is University of Texas at Austin, Team Dried. We are 5 minutes early, so I want to make sure our team's ready. if my helpers, Talia and Angelica, do you know if Team Dried is all here? All right, they are saying everybody is here. So we will go ahead for our final team of the afternoon. And this is the University of Texas at Austin, Team Dried.
Hello, everyone. We are Team Dried, which stands for Dryer to Reduced Instances of Extraterrestrial Delivery. This semester, we focused on modifying a small commercial dryer for operation in space. The team consisted of myself, Natalie Ozor, as well as Daniel Weber, Aleka Neptune, and Anna Blome. So the driving need behind this project is logistics reduction. Because there is no laundry system in space, astronauts have to pack and transport lots of clothes. Another issue we are facing is the dryer itself. Dryers take up a lot of room and consume a lot of power. On top of all of this, we were asked to modify for multiple gravitational conditions: orbit, the moon, and Mars. So to summarize, the purpose of this project is to modify an existing compact dryer to operate in 0, 1/6, and 1/3 gravity.
These are our requirements and constraints. They come from a mix of project requirements as set forth by TSGC, our sponsor interview, and NASA standards for human spaceflight. They represent a combination of functionality, geometry, safety, and project cost requirements. So the first step after determining our requirements was to find a suitable example dryer to modify. We have represented here 3 categories of dryers. The Magic Chef and Panda are small compact dryers. The Vivome is a mid-range dryer, and the Samsung is a full-size household dryer. So we ranked them based on the criteria cost, efficiency, mass, and volume. Cost was our most important metric because of our project budget of $500. Volume and mass were next most important because from our research, we found that it would be easier to make a small dryer efficient than to make an efficient dryer small. Because of these reasons, we chose the Magic Chef compact dryer. However, we did end up implementing some functions we found in the other dryers, such as the heat pump system found in the Samsung dryer. Next, we have our function tree diagram, which shows the main purpose of our dryer to dry clothes in various gravity environments, and the 8 main functions required to do this task. Because we are modifying an existing dryer, we focused our design efforts on 3 functions to first allow the dryer to function in space, and second, make it more efficient. The functions we focused on were collect lint, tumble clothes, and evaporate water. The other 5 functions were either already operational in the existing dryer, or many spacecraft have a system to already accomplish this function, as is the case with the remove humidity function.
For patent searches, we focused on 3 main avenues: lint traps, dryer dividers, and heat pumps. We focused in on these 3 areas because we really saw them as our main areas for ingenuity and wanted to make sure we weren't infringing on any other patents. For lint traps, we focused on lint traps that were geared towards repeat usage in self-contained spaces. For dryer dividers, we focused on dividers that seemed to have an adequate division of space and that still allowed for air circulation. And for heat pumps, we focused on heat pumps that were specific to usage in dryers.
As mentioned, one of the functions that we focused on was to collect lint. The goal being to reduce the dispersion of lint particles into cabin space because lint is a fire hazard. And the challenge here is that there's no gravity to pull the lint into a trash can when the user scrapes or peels the lint off the screen. So one of the solutions that we looked at was a disposable fabric packet. This would involve an initial layer of fabric over the air vent that would collect the lint, and then the application of a second fabric layer with a sticky border that would attach to the initial layer and enclose the lint in a packet shape. However, after some quick analysis, we realized that this was not cost effective and resulted in significant waste. So instead, we propose a modified cleaning procedure and a flexible roll-up screen. So instead, the user would initially or immediately vacuum the lint off the screen, or they would roll up the screen and transport it to a designated vacuum space.
So for the function of tumbling the clothes, we ended up deciding that some sort of dryer divider would be our best path forward. After 2 rounds of idea generation, we were able to narrow it down to what we viewed as our best option, which you can see to the left. This is our fan divider. It's composed of 4 vented fins that are attached to a motorized central dowel. In terms of function, these fins section off the drum and allow us to have compartments where clothes can be slotted in. And because of that motor, this whole system does revolve, so it adds an element of mechanical rotation. Now, to help prove that this was really the design we wanted to go with, we did some flow simulations. So you can see the image to the left, which is of our 0G environment. And the great thing about the revolution of the system is that it interrupts our initial airflow. So you see the airflow going to more parts of the drum compared to some of our other designs, where sort of only went to the top and the bottom. And again, because of this revolution, our flow patterns are a lot more chaotic. You can see some sort of kind of donut-shaped airflow patterns. And another major reason why we went with this one was because we didn't see any major variations between the different gravitational environments in terms of airflow.
So the previous 2 functions have been focused on making the dryer work in space. With the evaporate water function, we focused on making the dryer more efficient. We compared 2 main modes of dryer heating, resistive heating versus a heat pump system, and found that a heat pump system would be much more efficient. We also compared 2 different sources for the heat pump to pull heat from: the air in the room surrounding the dryer versus the heat removal system found on the ISS. In the end, we ended up using an air source heat pump system that pulled air directly from the room surrounding it, and found that that had a coefficient of performance of 5.99. So it was 5.99 times more efficient than a resistive heating element. We spec'd out a system that had similar characteristics and found that with our system, we could generate 50% more heat within the dryer while using 70% less power. The final change we made was to include a moisture sensor within the drum of the dryer to sense when the clothes were dry and stop the dryer to prevent excess power usage. One other change we made was the addition of insulation around every wall of the dryer. The thought behind this was to prevent excess heat loss through the walls of the dryer. We ended up using a 1/4 inch thick rubber sheet as our insulation, after comparing it to a 3/4 inch rubber sheet and vacuum insulation, and finding that those were both too large to fit within our existing dryer. We found that this added insulation would reduce the capacity for heat loss through the walls by about 91%.
We were also interested in modeling the dryness of the clothes as a function of time, and confirming the company's specs of 30 minutes to dry 1 pound of clothes. So we soaked a load of clothes and run it out to simulate damp clothes coming out of a washer, and then loaded the dryer and ran it. We measured the mass of the clothes at various intervals and found a linear relationship between the mass and the time that did confirm the company's prediction. This is our final dryer design. On the left is our bill of materials, listing the components for the modifications that we made, including the dryer divider, lint collection, and heat pump. And on the right is a 3D model of our final design.
So here is an example of a minimally functional prototype where it's placed inside of the drum. This does only have 3 fins, and that's due to some constraints within because of the shape of the drum of the Magic Chef.
And this is the dryer with our team patch that we designed at the beginning of the semester.
So these are our recommendations for future work. We think it would be interesting to explore a variable airflow model, which would also tie into our next idea for future work, which would be to compare the amount of heat that is lost to air leaving the dryer versus the heat that is lost through the walls of the dryer. We also think it would be interesting to design a custom heat pump compressor that would better fit within the geometry of the existing dryer.
So in conclusion, we determined that it is actually feasible to modify an existing compact dryer for operation in space with the purpose of reducing cost and logistical challenges. We determined that the dryer would save 120 kilograms of clothing over the course of a 4-year Mars mission, which equates to roughly $6.5 million in terms of fuel saved. These are the references we used during our research, and these are the image and part sources that you've seen during our presentation. Thank you very much for watching.
All right, thank you, Team Dried, and welcome. So, I see the audience is already asking questions. Let me jump right in then. Is there a typical vacuum available on spacecraft that could be used to clean the lint trap?
Yes, after meeting with our sponsor, he indicated that there would be a vacuum on space, which is a large part of why we transitioned from the packets to a vacuum solution for the lint particles.
Okay, and then you did mention lint is a fire hazard, especially on an enclosed spacecraft capsule. Is it safe once you vacuum it up, or does it still have some flammability? You know.
I'm assuming that the vacuum on the space station would have like an enclosed compartment for this particles, the lint particles that would be like disposed of safely. So I'm assuming that that would be taken care of otherwise, but not sure.
Okay, next question. How does the dryness sensor work?
Yeah, I can talk a little bit about this. So the dryness sensor works by comparing relative humidity between the inside of the drum versus the air around the dryer. And when the relative humidity is 0 or close to 0, the clothes are determined to be dry. So when there's no more air or no more water leaving the clothes, you can stop the dryer.
Okay, and do you know if in an enclosed system like a habitat or a space capsule, would there be any issue with taking the internal air through the dryer?
Well, sorry, what do you mean by that? Could you clarify that question?
So you had two different methods for taking air through the dryer, and one was just use the ambient room air. So if it were in a Mars habitat, for example, you'd be taking that breathable air and using it.
Yeah, so you would just measure the humidity of that air, and typically the spacecraft we've seen have powerful enough life support systems to regulate the humidity already at a pretty consistent level, so you can use that as a good baseline for your moisture sensor.
Okay. Next question online here. Do you see any drawback of adding insulation? Why don't manufacturers do it?
Yeah, I can take this one again. So typically, like most commercial large household units do include some sort of insulation around the dryer drum. It's just our small compact unit didn't have that already in it. So kind of for reference, like your typical household dryer is anywhere from like 4 cubic meters of drum space for like a stackable unit to 7 to 7.5 cubic feet, I think, for a larger non-stackable unit. And those do include typically some sort of insulation, but our unit is 1.5 cubic feet. So it's smaller and probably kind of cost, they cut costs and didn't include any insulation.
That might actually be a benefit. I mean, depending where you're at, you might want the extra heat to help you on the station. All right, audience, any other questions? Let me ask, when you were testing it, so did you always test it upright, or did you move it in different configurations to see if it would still work?
We always tested it upright.
Okay, do you see anything inside that would work differently in zero G?
Yes, so the interior of the drum actually has like these 2-inch sort of small fins, and it's not so much that it would work differently, it just they no longer have a purpose in zero G. So what those do is when clothes sort of hit up against them, they help sort of push it up, and then gravity brings the clothes back down for a tumble function. And just because you don't really have gravity when you're in outer space, those fins just no longer really have much of a purpose. So part of our final CAD, we actually remove those just because they're less necessary.
Okay, so you move those and put the fan system in?
Exactly, yes.
Okay. All right, so let me ask you, what were your biggest challenges this semester?
I can start. I think being online just presents a lot of challenges, especially when you're trying to do a hands-on engineering project. We were fortunate in that Anna and I actually lived together, so we were able to collaborate on some of the more hands-on tasks like that. But overall, I think you're generally able to accomplish more in a more efficient way if you're able to be in person on a regular basis.
To add to that, I think another issue for us was figuring out how to really verify that something would work in zero G. So an idea we had was to put our model in water and see how it worked, but it's a little bit hard to test out dryness when you have something fully submerged in water. So that was a little bit tricky to think about how we're going to work it, and we ended up relying a lot on software to help us figure out what we wanted.
Yeah, I think another one of the challenges is like the online nature causes you to divide up tasks a lot more rather than collaborating on them. So we all kind of had, different subsystems we focused on, and it took more time to get each other caught up on those because we weren't necessarily working on them together.
All right, so any final things you're going to do before you call this a semester?
I think we're pretty much done for the semester, although if we had maybe another semester to work on this project, some future work that we were interested in would be customizing our heat pump. So the heat pump system is a lot bulkier than a resistive heating element, and so that expands the total volume of our dryer system. So if we had more time, it would be interesting to see if we could customize the shape of that to fit within our dryer specifications.
I think one of your earlier questions was about like testing the fins that we designed as well. So with more time, we'd of course want to run more experiments and then figure out, I don't know, maybe some way to work around the submerging problem to simulate the gravity.
All right. Thank you, Team Dried, very much. All right, so this concludes our afternoon for the Design Challenge. I want to thank, of course, all our team faculty advisors and NASA mentors putting in so much work to support the students, all the collaborators that they tapped for additional help. Judges, so we do ask that people judge the posters and the videos online. So all the teams were emailed links to that. Please take a look at that. I want to thank everybody online here in YouTube. Your showcase audience has been great, asking lots of great questions on Slido. And of course, all the students. We've got 10 teams tomorrow. We had 10 teams today. All of you had put in a very strong semester under extra difficult circumstances. We do have a meet and greet for some teams from 5 to 6 tonight. We have emailed all the teams that link. If anybody is online that would like to go try to meet some of the teams, please email us at designchallenge@tsgc.utexas.edu. Just say a note that you would like to join the meet and greets, and we will send that information to you. All right, thank you all for watching, and this concludes day 1. We'll see you tomorrow at noon. Have a good evening.